presentation?
I can try.
So I will give you the presenter option, and then you can try to use the system. You're a presenter now.
Okay. How do I present this? Okay, one second. Oh, share my screen.
Wait, are you presenting? Okay, sorry, I just jumped in. I just heard presenting. Are you demonstrating code or something to share, or just have slides?
Just slides.
Then they should be uploaded. You don't need to share your screen.
Oh, okay.
Yeah.
Gotcha. Cool. Now we'll just stop sharing.
Yeah, the sharing screen is a lot more network intensive.
Okay. Yep.
You can change the slides in the plus sign in the bottom left side of your screen.
Oh, I see. Oh, sorry, I was changing.
Yeah.
Okay, I see.
Yeah, but you can select also your own presentation.
Okay, where's my own presentation?
If you go to manage, it should say like manage presentations.
Manage a presentation.
And then it'll show you. You'll be able to pick a. You'll see a bunch of presentations in a window would pop up.
I don't see managing my presentation.
In the you click plus. You don't see manage presentations.
I don't see plus. I see minus.
No.
Oh, I
plus
see.
On the bottom in the actions.
Got it. Okay.
Well, we would. The beginning of the microconference should start with the default slides, and everyone should thank the sponsors.
Yeah.
Okay. I just okay, I got it. Oh, I see.
And then Daniel, how about if you're going to start the introduction of the conference, and you might thank all the sponsors, and then go in and switch it to the next presentation, and then that way the presenters don't have to worry about switching presentations.
Yeah. No, I will do the introduction, or maybe the VOD. I didn't see him online yet, but yes, we will do the full presentation, talk about the sponsors, anti-harassment, and do some instructions, and then I'll try to switch the slides myself.
Yeah.
From one presenter to the other, so to avoid this kind of complications.
Okay. I just noticed that the eBPF or the BPF track has BPF tracing for the first session, so I might actually jump to that one. I might miss the beginning.
Yeah. No problem.
Oops. Okay. I think there's an issue. There's a two, so exactly same slides. So so my first topic is the wake polling. The second is the LLC get domain thing. So I think, yeah, my second one's probably wrong right now.
You can. I got the presentations from the LPC site.
Okay, let me check it.
Yeah, you can upload your presentation as well.
Okay. I probably.
It takes like a minute. So if you have a PDF available right now, PDF is the best format to upload in. So if you have a PDF available right now, you could just go. There's a place to say upload. Just select your file and upload it.
Okay. Yeah. I think the slides under my topic is correct. So if you look at it, this two, number 2, number 3, it looks exactly the same. It's the exactly same slide. So the number 3 should be let me see. Should be the LPC 21 SDLC legal check.pdf.
Also, if you want people to download your slides, in that manage slides, there's a little download, or that little like square or rectangle bracket next to your slide name. There should be like the where you would pick where to select it. If you select that, you'll allow people to download your slides as well.
Okay.
I wonder, Daniel, I wonder if you should just have that happen, enable that for all the slides.
Okay, I will do.
You guys don't hear any background noise from me, do you?
No, I don't.
No.
So the echo or whatever the background noise thing is correct. Someone has a chainsaw next door.
No, we
And I'm
can't hear
outside.
anything.
Pretty impressive noise cancellation. It's very loud to me.
Are you done, Leo?
Yeah, I'm done. I just want to point out that number three, slide number 3 is wrong. I have the correct one under my my second topic, the new challenge in using LLC scale domain wake-up path.
Sorry, I didn't get. I've uploaded your 2 presentations, right? There's the first
Yeah.
talk that you give and the second talk that you will give. Which one?
Yeah,
is
there are 2 different presentation material if you click in. Let me share the, let me add you. I can send private message to you.
Okay, mail me the presentation you would like to change, and then I can change myself.
Yeah.
Oh, I see. The 2 presentations have the same name.
Yeah.
I was able to download from the site. It was my fault. I've uploaded the wrong one. And I upload it now. Correct.
So Daniel, I'm going to switch over. If you need anything, like for the first session, like I said, I'm going to be jumping back. I'll be jumping back over there. Ping me on
Okay.
IRC. That might be the quickest way.
Yeah, but things are under control here.
Good.
Will you need to add me as moderator, or can Daniel do that?
Wait, you're not. Let's see. You're not a moderator.
Yeah.
No.
No, you. That requires, I guess, one of the. I'll go.
Promote to moderator. I promoted Davao.
Oh, okay. I guess
Yeah,
you can
there's
promote
an
to
option.
moderator. He should have been moderator regardless, but
Actually, Daniel, I was supposed to be a moderator as well.
Yeah.
Yeah, if you could add me. I don't know what happened. Thank you.
and just be careful. I don't know if moderators have the button or not, but I do. But when I exit, underneath it says end meeting, leave meeting. Make sure you hit leave meeting and don't hit end meeting.
Right.
I think the moderators may have that option, so please be careful when you exit a session. And sadly, the 2 are right next to each other, so you can easily make a mistake.
So is it just me, or is the Matrix chat not working either directly or through Big Blue Button?
Yeah, it's not working for me either.
Yeah.
Which metric the value is speaking about?
Neither shared notes. Oh, shared notes are working.
Right, that's working, but the chat is not.
Helping Stephen.
The chat loaded for me after a few retries. It's really, really slow.
Yeah, I think it's Stephen. He probably has more. Okay. Okay, Stephen said that it seems that there is some load issues with Matrix, and he will check it out. So just have to wait. Anyway, should we start?
Yes, we should.
Yes.
So, welcome to the Linux Plumber Conference 2021. This is the scheduler micro conference, and I'm glad to see so many names that I'm used to seeing face in conferences, but also new faces in the community, which is always good, right? So before I start, we would like to say thanks for the sponsors. We have Facebook as Diamond sponsor of the Linux Plumbers. We have IBM as Platinum, ARM and Microsoft as Gold sponsors. AWS, Netflix, and Red Hat as silver sponsors, and Collabora as a speaker gift sponsor. We always like speaker gift, and VMware as t-shirt sponsor. Also, Linux Foundation with conference services. And so, before I start, we know that discussions on Linux community sometimes get warm, but let's keep it technical, let's keep it friendly, and let's behave, right? Let's make this a nice conference where everybody can speak and give their own opinion without any kind of fear or anything that blocking anyone to say their thoughts on the technical talks. That's what makes our community what it is, makes Linux a successful project. And yeah, if you have anything you would like to complain, please ping us, and let's find a good way out from any discussions. But any word, Daval? Any word, Vincent, Yuri?
I think we just want to clarify how to how to ask questions, how to point out you have a question to ask.
Okay, sorry. You mean you would like to clarify with me to?
So because this is a virtual conference and chat doesn't seem to be working very well for most of us. The best way, the protocol we followed last year, and I think we should follow this year, is if someone has a question, just turn on your camera. So one of us will know that you have a question and we can bring you in as quickly as we can. Depending on the speaker, feel free to interrupt if you think it makes sense. And all the good rules we have followed at LPC in the past.
Yeah. So yeah, just this housekeeping note here. Please keep your microphone and camera muted when you're not actively participating. But as soon as you want to speak, you have any topic, just turn your camera on. That's the sign that you would like to speak, or just turn the audio on and say, hey. Any thoughts, any questions? Should we start?
Yeah, I think it's time to start.
Here we go.
All right.
So, last point. I would like to ask you all to help on taking notes of the conference. The organization will ask us for the notes, so people that didn't participate could read it through the news. So everybody that's participating on discussion, which is or trying to learn, if you have time, please help us taking notes. And that's it. Now I give the word to Francesco. Just let me make him the presenter.
Thank you.
It's all yours.
Okay, thank you. So, hello everyone. I'm going to talk to you about migrations and propose you a tool that could help you investigate them. I worked with Dr. Dario Fagioli and Professor Enrico Bini, who I'm pretty sure you know pretty well. My name is Francesco Giraulo. I'm a master student in computer science at the University of Turin, and I did my bachelor thesis on migrations flag, and I'm still working on migrations. Okay, our problem was to try to find out the root cause of migration inside a system, especially because during the previous research on the flags, we were not able to have really accurate results because we didn't know the migration cause of the bunch of migration we found, and we needed something more accurate than just some quantitative results. So we try to find a way to get the causes in a direct way. By now, the only way is just to manually dive through the records of a trace command report, for example, and try to investigate the reason. But it's not really scalable for a large bunch of migrations. So we want to try to find a way to automatize it. Actually, I'm trying to code something, a tool that could help it on it. And in its first level is trying to add some depth to the record representation. Its first level is trying. Okay. And basically modeling the data offered by the record string, offering both a common API for example, core or timestamp, and something more specific to the record type. For example, the source or destination core in a migration, or the process names in a switch. Another interesting point is to merge the continuous information spread across the report. For example, an easy point is to collect the record and its stack trace that are actually in separate records, or try to collect the data from function graphs, start entry and exit point of a function, and try to define a more fine-grained filtering in order to filter the specific, for example, migrations record better than the switch records. By now, the tool is offering an interactive research support, helping the user to get the next record that is filters compliant, and keeping some information from the skipped records. Well, they are not actually skipped, they are collected in a history that could group them by core or by process name. And the semantic information we can collect is basically everything, because, for example, we could collect the last process switch in if we have the switch events recorded, or the quantity of time the CPU was idle in the time window. And yes, the tool is able to offer also some statistics from the whole records, for the whole report, or for some time windowed or process related information. Of course, we want to do some step more and try to find the patterns or the logic to label the root case of migration in an automatic way. Okay, the way the tool is working is basically object-oriented. So we can build some composite objects over the records, splitting the common parts and the specific record type, handling the trace like a stream in a functional like framework, and in a similar way we can make the stream flow through some stackable and customizable blocks that are the one collecting the semantic information, for example, or collecting the traces or filtering the records themselves. Okay, by now the tool is basically a library with a simple terminal interface. And for example, we can see some output from the use case I will show you in a while. And for example, we can just try to filter the scaled migration task that is related to PID for a specific PID and obtain the running task in the moment of the migration and the idle time. Our use case was to try to analyze the migrations of a while one process, so strictly CPU bounded, in an unloaded system. So we were assuming that the process will not migrate so much because it will never leave willingly the running state, and no other processes need more CPU that is available because basically all the cores are idle. So we were supposing little to no migration should occur. Unexpectedly, the number of migrations is not negligible, and some of the migration could seems counterintuitive. In fact, well, we have here just some data from the use case tested on the last kernel version, and we can see how even if the migration of a CPU bounded in a loaded system should just add overhead, is not always the case. In fact, the mean time, running time of processes that are pinned to a core, so they are not allowed to migrate, is usually higher than the free to migrate tasks. And we are not sure about the reason. But using the tool, and you can see the bottom part of the slide, we add, for example, for this migration, the one in the top, there is no actually task who needs the core. In fact, the while one process is migrating from CPU 4 to CPU 10, and the first process that is entering the CPU 4 running is just 2 seconds after the switch. So it cannot be the reason. So it should be related to the balancing, but balance to idle core could be at least unexpected. So well, this is an insight about the tool, and of course we wanted to study more the migration of while one, but we need more time. So I think I said what I need about the tool and the use case. I would love to hear your feedback about how if the tool could be useful and if it would be worth it to try to make the labeling automatic. So thank you.
I have a question for you. So have you been able to find the root cause, or did you say that you haven't found the root cause of this while one?
Okay, I didn't find the root cause. We are thinking that the point is balancing between the cores, because since we have no task who actually need the cores, we think it's something between the balancing. We have no other causes.
Okay, and just for me, how do you plan? I'm not sure I have catch. How do you plan to label the migration root cause? I mean, when you have identified that task migrate. So you want to label that about why the migration occurs, but which kind of label do you want to put that?
Okay, the idea was to try to find out, for example, if a migration is caused from the balancing, or if it's caused by an exec, so or other causes. Because since we are, at least I'm coming from a flag related research, I want to understand if the migration are occurring for one of the causes related to the flags, or for I would say normal condition. So it's just to understand better.
Okay.
So this kind of reminds me of our talk last year on whether the Oracle database should be using real time or not. And one of the things we did notice was an extreme number of migrations. I wonder if this could help with that.
But by now it could not, because it is not ready for a real-time execution. But I was talking with some. We were thinking to just move it in a more, I would say, live implementation in order to be used in a real-time environment. But by now,
by real time, you mean real time or Twitter likely real time?
Sorry?
By real time, you mean actual real time or Twitter like real time? You know what Twitter means when they say real time?
No, I mean, I think I mean not real time.
Okay,
Yeah.
so no,
Okay.
we are running the Oracle processes as sched other. We're not running
Okay.
them as real time. When we are running them as sched other, even
Okay.
on systems that should not be heavily loaded, they are migrating a lot.
Okay, so yes, that could be. I mean, if we continue the developing and we actually find a way to automatic label them, I mean, we need to find the patterns, or at least the logic behind the migrations in some specific case in order to make it automatic. And after this, yes, it could be sure. I'm sure it could be useful.
Okay.
So did you look into active migration? I think active migration is what is causing just like idle processes to, at random times, just steal other idle processes. I'm not to steal other processes that are just running by themselves.
Yes, this is one of the okay. In the first stage of research, we found out that there are some patterns of a core try to stealing from another core just because it's idling. But in some cases, there is something like, okay, the core who is running or while one is just pushing away the task because, I don't know, some kernel-related task or driver-related something really quick is using the CPU. So we wanted to investigate if that is really useful migration. So not just the active migration, but even the migration that are not, I would say, not intuitive, because if a while one process should run on a core forever, basically, and if just a driver is taking few time slices, it's not a big deal, and maybe should not be migrated. I don't know if I answered your question.
Okay, so I mean, I was just thinking of the case, I often see that a idle core will just, every now and then, will just steal a thread from a core that is running only one process.
I didn't hear you pretty well, sorry, can you repeat?
I often see that an idle core will steal a thread from another core that is running only one process.
Yes, it's happening, yeah.
That's your situation also. So I
Yeah.
think that's the active balancing, where a core feels frustrated that it's not able to steal anything recently, and so it just steals something. So
Okay.
you can look and see if that's your situation. I was also wondering, like, kind of annoying thing is that there are four, to my recollection, aren't there several different occurrences of the migrate task event in the kernel?
Sorry.
Are they? There's, as you point out, there's different reasons for having a migrate task
Yes.
event. And I wonder if you could suggest that we have maybe some different trace points to indicate what the different situations are, or different arguments of the trace point, or enhance the trace point in some way to indicate something about the context.
Well, but by now I'm not sure if we need some more trace points, because I had not. Okay, I was not able to find out the root cases. So maybe with some trace point, it could be more easy. But by now, I'm not sure, because I didn't dive so much inside the code. I worked more on the behavior of the system. So I need to check more the code. And if it's the case, to try to figure out a way in which put the trace points. But by now, I didn't consider that thing.
Okay. It's just that load balancing is quite a different thing than when a process just wakes up and wants to go to another. It's just getting put on a different course. So it could be more intuitive to have more different trace points.
Yeah, I mean, yeah, that could be surely a way.
Okay.
I will keep note. Thank you.
Okay, thank you.
This is Shrikar here. I would want to know if can't we use the callbacks, right? When the tracing callbacks, if we have enabled the callbacks, then they could tell us why we are calling the migrate, right? For example, in the like what Julia said, in the active balance, we would have seen the callback suggest the active balance, and if it was from a wake up path, we will get to know the signature that this is from a wake up path. So can't we use the call graph stuff to do this?
The audio was not so clear. I'm sorry. Can you repeat?
Okay. What I was saying is, if we have enabled the call graph stuff, right? When we are tracing, if we have enabled the call graph, the perf would give us the stack trace for each of the trace, right? So for each of the stack trace of sked migrate task, if you look at the call graph, we would be able to associate the reason why the migrate was done, right?
We should be able to.
Maybe if I understood correctly, I think you, Srikar, are suggesting to enable the basically stack trace call graph for every trace point. So then if you have a migration trace point triggering,
yes.
then you also have an associated stack, and from there maybe you can understand, but I guess it's going to be a tricky process. Not sure. That is an option, I think.
Yeah. Okay.
Yeah.
Yeah. Okay. We tried this as first try. Okay. The point is that even with the stack trace, or even with the function graph, there are common points between all the migration causes, and the differences are based on, I mean, arguments of the functions. So we are not sure just from the stack trace to understand which is the real reason. And sometimes the reason is not inside the stack trace itself. So that's the point of the tool, try to merge out the data from maybe several stack traces or the state of other functions or events, and try to get some big picture of the migration itself.
Yeah, I guess, I mean, personally, it's been a while actually that I worked on strictly on understanding the load balancing on CFS behavior. But for what I understood, also from what I recall from mostly working with Dietmar, was that we had basically additional print case that were basically printing kind of the reason why migration happened during a particular workload. So I probably think the idea of adding information to the trace points, I'm not saying that we need to modify the current one, but we can probably attach a different one or attach more information to what we have, and it might help, I guess, in some cases.
Okay, yeah. Thank you.
So can you hear me?
Yeah.
I think what you might find is that the migrations are correct, and then the real question will be, how did you get into that correct situation in the first place? And some things that I've seen are that there are tasks bound to certain CPUs or hardware interrupts, and so you've got your while one loop trying to run, but this other thing has taken over the CPU, and so it's perfectly natural for something to get, you know, a K soft IRQD is running, and you're now queued up behind him. He's going to get pulled onto another CPU, which is a perfectly natural thing to happen. So the real question is, well, did you really have to run that K soft IRQ in the first place, right? So it's working properly, but you're not necessarily going down the path that you thought you should go down, right? You would think, hey, I should have the CPU all the time. So I haven't found any malfunctions, and I think you may perfectly illustrate what I'm saying when you're done, that it's working properly, but it's not working exactly the way expected because unexpected causes are behind the migrations, right? I don't think that I doubt very highly you're going to find erroneous migrations. You're going to find correct, unexpected situations that caused correct migrations. Does that make any sense? So
yeah.
The real problem is, hey, migration sounds like a great idea if you're going to be stuck in the back of a queue for a long time. The problem is you don't know if it's going to be a really short or really long. We don't know. And meantime, you've got an idle CPU saying, hey, give me work, give me work. So he grabs the work, and that's the right thing to do, but he didn't know that you were going to be done so fast. So then the question is, oh, is there a way that we can indicate we should be done so fast and we shouldn't do that? And maybe that would be an enhancement.
Yes, okay, I got your point. Yeah, I'm pretty sure that there are not erroneous migrations, but my idea was actually to find out why I was not expected these migrations. Of course, it could be the point of a quick job is just keeping the CPU for a short time, so it's not the case to migrate, and that could be, of course, difficult to indicate. The things that make me more that makes less sense to me, but in an unexpected point of view, is just the migration. The migrations are often a source of ping pong between two hyperthreads of the same physical core, and it's not something like I would say one shot. So
yeah, I've seen that too. That's common, but that's not necessarily a bad thing because they're sharing the same L2. That's actually terrific, right? So you've got say you're on CPU 0 and 1 and they're hyperthreads. You've got your bound thread to CPU 0. You are running on CPU 0. That bound thread kicks you off. You run on CPU 1. That's actually the optimal result. That migration to CPU 1 is actually perfect. There's not a better place for you to have gone, right? And then,
right.
But then the awkward thing is, well, in some cases, depending on sort of which flavor of the scheduler we're running, you might, when he stops running on 0, migrate back to 0, and that's completely wasted migration. That's just extra cycles, but at least you're still sharing the same L2, so it's not so bad.
Yes, of course, but I mean, it's the number. It's like in 5 minutes trace, there could be even 25 or to 30 migrations. So of course, it's good that they are close enough, but maybe some of them could be avoided. That's the whole point.
Yeah, I'm more okay with the migrate out than I am with the migrate back. The migrate back was wasted work, unless something really wants to run on CPU 1 in that case. Probably at the end of the day, what you want to do is total up the cycles that were due to the migration. I mean, you can't really count for loss of cache hotness, but you can total up cycles, and you can actually, say, great, how much tax am I paying for those migrations? How important is this problem? Because on a graph of where stuff runs, this looks like, oh, this is a huge sin to migrate, but a migrate in 20 seconds, I'm not too worried about a migrate in 20 seconds. That's a really small percentage of cycles.
Okay. Thank you.
So a question, Francesco, more from the, let's say, from the academic side.
Okay.
Did you try to identify and classify the reasons for a migration in a more high level way, to try then to put things on buckets, right? Okay, this kind of migration exists, it's good. This kind of migration exists, it's bad. It's good to migrate because of power savings. It's bad to migrate because of power savings. Because you're finding migration, right? And you try to define the root cause of them.
Yes.
But did you find the possible root cause? Did you try to classify them and try to classify them with other reasons, like if this is good, this is bad?
Yeah, the idea was starting from the root cause, try to figure out if the migration is good or at least how good it is. So yeah, this is the next step. But since for me, the situations are often completely unexpected, the migration. So I wanted to start from something more low level, understand the environment, let's say, and after this, try to put some things in the buckets: good, bad, not so bad.
Yeah, I think that would clarify. Will give you better direction to the research, right? Because then you would be able to use the tooling that you have to do this kind of tracing, to find some more, let's say, some useful information from the trace you are getting, right? Because the root cause for a migration might be good to someone, it might be bad to other case. There's a reason for the things that are occurring.
Yeah, so there's bugs. You may find some bugs, and that's terrific. It's not super likely that you'll find some bugs. The real question is, okay, what if the algorithm is correct, but you're migrating so much that you're spending a lot of cycles migrating, right? Or it doesn't seem like you're spending a lot of cycles migrating, but the things that you've migrated have lost their cache footprint because they used to be running over there. So you sort of have to quantify how important it was, A, the number of cycles that you used migrating that maybe you could have avoided, and B, what was the actual performance impact of migrating? So you're going to need something more clever than a while one to notice that impact, right?
Yeah, of course, yeah. Yeah.
And measure that. And that's really the cost that you could optimize and fix, is that performance impact.
Yeah, thank you.
Yeah, so another workload that we were playing with TBCC, we noticed that even though the CPU itself is like really busy, but sometimes like the workloads like sleep for a short while, say doing something, and then wake back up again. So ideally, you probably don't want us to migrate, do the migrations, because that CPU is going to wake up and service again. But in reality, we noticed that the tasks actually get pulled around quite a bit. So one thing we play around with is that we noticed that the idle load balancing does not has a very like almost immediately try to pull tasks. If a CPU becomes idle, it start pulling tasks right away. Yeah, it does not realize that, oh, like just a microsecond later that I will be busy again. So it start pulling tasks. So we find a lot of migrations due to that reason. So yeah, so we play around a little bit with like checking the the business of the CPU is at 95%, then we give it a longer idle, like load balancing interval. So it does not try to pull task right away, but wait a little bit. Yeah, and we find that helps. Yeah.
Yeah.
Thank you.
Yeah, and so along the lines of what Tim said is he's pulling onto what's an instantaneously idle CPU, but then something wakes up that used to run there, and now his CPU is busy, and he has to move somewhere else because the in is full, right? So if you run, say, netperf, you'll see this all the time. If you load balance instantaneously, a packet will come in and say, hey, wait, I was running here. Oops, prev CPU is now busy. I have to now run somewhere else, which sucks, right? It's really bad. And on that workload, you'll really notice it.
Yeah. Thanks, Francisco. It was a nice presentation. It was a nice discussion.
Thank you.
So we'll start a 5 minutes pause. Everybody go to get a coffee for the next topic.
Okay, so it looks like people are starting to be back. I'll bring up the next set of slides. Lebo, you should have a presenter powers right now.
You are now.
Okay, let me turn on my webcam. Okay. 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 Cool. Can everybody hear me?
Yes, we can.
Yes. Oh, okay. Awesome. 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 Cool. So my name is Lebo. I'm from Oracle Primary Working Scheduler. I'm relatively new on this field, so do correct me if I make any mistake. So I plan to quickly explain the problem as detailed as I could, and leave most of the time for open discussion. Okay, so we do have a few people here who are familiar with the problem, so do jump in if I miss out some important details. Okay, so let me get to the problem. So basically, before I describe the kind of the symptom, let me show you how to reproduce this. So basically, you won't have interrupt heavy workload. So that could be like any kind of web server application. We found out this problem using the YSSB. Also, you can reproduce using iProp. The goal is to create many interrupts, particular network interrupt, as many as you want. So the second condition is you want to bind the network IRQ to a specific socket or Newman node. So, so the reason for that is, so this is actually a very common practice that the network performance is very sensitive to having IRQ routed to the wrong socket. What that means is oftentimes the PCI bus is direct connect to one socket, the PCI bus and PCI bus bridge. So you actually will get very bad performance if you have if you route this network interrupt to different socket. So I found this like a 2 times slower performance. But we do not see such a huge drop in performance, I think. But also, and the flash performance, by the way, the flash performance is not very sensitive to that. So that's kind of interesting. So basically what we saw is tasks like getting pulled to the socket that the IRQ bound to, okay? And leaving like the other socket nearly idle. You can also do that on an AMD current chip, like basically bind the network IRQ to just one Newman node. So, and the rest of the Newman node will be like almost idle, right? So within that socket, the load is actually fairly balanced. So, I would, right, okay. So if you kind of spread out the tasks using like using binding like task set, or maybe tweak the kernel to spread out the task with across sockets, we actually see performance getting better. The YSFB throughput getting better, especially on the light load. On heavy load, it's a little bit we're still trying to investigate that. So yeah, this is the MP stat from the on the light load. So CPU 0 to 23 is the first hardware thread from the first node, and 48 to 71 is the second hardware thread. So this is the Intel chips. You see the task mostly just one node, one socket, the first socket. Okay, the rest socket mostly idle. This is from light loaded system. From the heavy loaded system, well, it's the other socket is not completely idle, but you see the idle times, like the idle percentage like 60, around 65 to 70, and the first socket is like pretty busy, and also you can see the 40, 50, CPU 52, 50, CPU 22. Those are the CPU that the network IRQ are bind to. So that's why you guys you see this very high software IRQ usage. Okay. What is the cost actually? So it's actually the CFS wake ups, like actively pull all the wiki tasks in, right? So so because there's a very frequent wake ups from the network interrupt, because of network interrupt, and also the network IQ binding, because we have this our system, we have a static IQ binding, but you can also do with kind of dynamic kind of range bind, but bind to a one socket, so that the network interrupt will like mostly happen on those CPU on one node or one socket. So the wake up will pull the task in. We also notice that it actually actively working against the periodic and the other load balancing. How that happens is because you have such a frequent interrupt, and you have this complete school of loads. So one socket have more load, and then the load balancer actually notice that, the periodic load balancer notice that, trying to pull the task, move some of the tasks to the idle socket. But the moment you move that loads, because the wake up is so frequent, so the wake up will quickly pull that task, move the task back to the the first socket. So the socket had the network IRQ binding. So that's kind of like ping pong. It's not it's kind of bad. It's really bad for the performance. So we look at the code, trying to understand why the wake up is like pulling out tasking. So basically, the wake up will the save of the wake up will call the select task run queue fair, which has like two pass process, like determine whether to do wake up find or not. So this is the wake up find actually doing. So if the wake up decide to do wake up find, then it will put the task in, right? So that's how basically what happened. So the two processes, the first is they have the wake wide, the first pass, basically a heuristic to determine if you want to spread the you want to do wake find or not, right? So if the wake wide says, no, yes, I want to do wake wide, then you will go to the second pass to determine if we still want to do the wake find or not. So if you look at the heuristic, it kind of makes sense if the kind of the waker and wiki are somewhat related. So for example, the waker wiki, the waker holding a lock, right? And the one after he release the lock, you want to wake up the wiki who trying to grab the lock. So that kind of makes sense. But when but with the interrupt, it's kind of it's pretty different, because the interrupt happens. But the waker is actually not the waker task is actually not the one actually wake the wikis, if that makes sense, because the waker task is actually the one who is running for completely different reason, and the interrupt came in right on this CPU that waker is on, and they decided to let's we have the network packet in, then let's let's wake some wiki up. Okay, so the wake wide thing, the wiki flip number, just the compare between wiki and wiki just doesn't make too much sense, because they're not related at all. So what we found out is actually the wiki wide is almost always return 0. So basically means like do wiki find, because we notice like wiki actually have a very similar wiki flip, even though this very significant like imbalance, right? So the second pass is the wake find. So we notice that wake Y actually is more dominant than the second pass wake find. Wake find is like a wake find idle and a wake find wait. So sorry, Vincent, do you want to jump in?
Yeah, I have a question for you. So
yeah.
Your problem is between two NUMA nodes, and you're mentioning wakefin. That's it?
Yeah. Yeah. So basically, what happened is you have the selector task run fed look at two candidate CPU, right? The first is the weaking CPU. The second is the previous CPU that the wiki was on, right? So it will try to make decision to pick like one of this. So wake up fine means let's pick the waking CPU. So what happened is with those two conditions met, they always the wake up always do the wake up fine.
Yeah, I was just because there is a case where the wake caffeine is disabled between NUMA node, and it's mainly linked to the what we call this reclaimable distance. So if the wake caffeine is one of your problem, I wonder if it's mainly because it should not set for in your case, in your topology. I mean, if that make the reclaimable really heavy.
So you're saying just completely disable wake fine?
I wonder. I mean, it seems that the wake fine for you is painful in your system, and I wonder. Is it only for this use case? Because it's not normally the wake caffeine is not set for all the NUMA level. That's my point.
Really, I think I thought it's always set for wake ups.
So we have a reclaim distance above which we disable the wake caffeine.
That I need to take a look at because our Intel system, so two-socket system, I think it was always on. And sorry.
Yeah, the point is that I was looking at the code and the reclaimable distance is 15, which means that I agree that if your distance between your two nodes is below 15, in this case, you will set the wake caffeine. But isn't maybe your problem is that your node distance is not the right one?
Actually, I kind of disagree. So the problem also is, well, let me get to the fix. Like the question I want to ask is ultimately when we should pull for interrupts, right? So it's a decision that wake ups need to make. So ultimately, you look at two candidates, the waking CPU and the previous CPU, right? If they're from different NUMA node, who has the warmer cache, right? That's a decision we want to make. Also, we're trying to have like balance the load across NUMA node. So I don't think the scheduler has the information necessary to make that decision, like, right? Because interrupt coming, it may bring the packets, for example, network packet, may bring the network packets that the wiki wants, but sometimes it doesn't. Sometimes the old CPU actually got the warmer cache because it has run on the CPU before, right? The other thing is, okay, so can we like allow the user space to say, okay, I want to, do polling for our tasks during wake up, right? So that's the second question. The third one is actually the wake wide thing. If you look at the code, it compare the wiki flip between waker and wiki, right? It just didn't make sense for like a wake up from the ISRs. So my question is, could we have a somewhat better heuristic for interrupts? Yeah, that would be my my presentation. So please jump in. Okay.
I think for the wake wide right now, this has been done. I would say that's the least worst solution. I mean, we have this. It's a long problem about should we wake wide or not, and the proposal that have been made a time ago was working at that time. Now, I mean, if there is a better proposal, I would say make a proposal for another wake wide mechanism. That's if you think that there is some better way to detect when we should wake wide or not.
Yeah, I mean, I think it does make sense for certain like workload, but the struggle is like we want this to doesn't hurt other workload, well, like benefit some some workload. So yeah. Any other? Please jump in.
So Barry
Yeah.
had a question.
Okay.
Yeah. Yes. Can you hear me?
Yeah, I can hear you.
Yeah. We have seen exactly the same phenomenon with you. Recently, we are running my cycle on a 4 Luma load machine, and the Luma 0 get a Ethernet card, and the Luma 2 get a storage. And if we are running my cycle, what I've seen is Luma 0 is busy, and the Luma 2 and Luma 3 are also busy, and the Luma 1 almost totally idle. So I think it's the same problem with you, just like the interrupter happens on Luma 0, and then the workload are put to Luma 0. But I think maybe it's the same reason the wake-wide always decide to pull the task from Luma 1 to Luma 0. But the things I don't understand is that you said in night load, actually, if you disable wake fine, you are saying performance improvement. But in my understanding, if you have night node, actually one Luma is quite enough, right? Your load is light, your load is not busy, so one Luma is quite enough. So in this case, I think maybe polling tasks should give you bad performance, not worse performance. That's the first question I have. The second question is actually, I think maybe pulling a task to the Luma load is running, maybe is a good solution because you still get some case affinity. For example, you get a package from Luma 0, and then you run a thread on Luma 0, then you get a hot case for the socket buffer. Yeah, so that's what I don't understand why you
Could you explain the second question? Sorry.
Second?
Yeah. Could you explain the second question? I didn't get the
second question is actually, you said interrupter and the threads are not related, but for me, they are related because, for example, Luma 0 has a Ethernet, and the Luma 0 get a socket buffer, get a socket package. And if the threads are also running on Luma 0, you got the hot case for the socket buffer. So why are you saying they're not related? In my understanding, yeah.
Okay. What I mean is, if you look at the wake Y, I'm not saying polling to the that CPU is not. I'm just saying to look at the code, the wake Y thing. They compare the wake flip. So the waker actually in that case is just the CPU running on the task running on the CPU, right? So the task could be any task. It's just not the one actually wake the wiki. So comparing the wiki flip between the waker and the wiki, it's just, to me, it's just, I don't see how they're gonna relate it. What I mean is, if the waker is actually the waker, right? The waker is actually doing like the one actually wake the wiki, then the comparison actually does make sense. So the first question is, to answer your first question is that, yeah, I thought that was really weird because on the lightly load system, actually, polling to the interrupt CPU actually should give you better performance, I guess. But also the other thing you want to think about is that does the incoming packets actually give you warmer cache, right? So for our YSSB, for example, each task will, so the client send a query to the server. So the server will, okay, let's do process the query and send the result back, right? So the client will, I get the result, then we'll send you another query. So that's the incoming packets, right? It's the, could you, we got your result. Could you execute this query? So if you do that kind of comparison, you will notice actually the old CPU actually may have the better cache, right? Harder cache, because it's the CPU that actually, it was the CPU actually executing all the query, load the table, scan the row. So that's my theory. Yeah.
Yeah, so I just want to say that this problem is quite real. We have recently have very big customers that actually ran into this problem. They have a big NUMA imbalance, and the reason was because they put all the interrupts on the NUMA node where the network card is on, right? It's natural to configure things that way, and because of the imbalance, they actually get worse performance. So they have to spread the interrupts to kind of mitigate the problem.
Yeah, I think the whole reason they won't do that is basically because like I said, like the NIC, the PCI bus is connected right to one socket, right? So they feel like it's they actually will have better throughput if the interrupt is on the correct socket. So this is the whole yeah, I totally agree. It's yeah, our internal customer also have see that many internal customers see that problem. Thank you.
Julie.
I'm not clear on why you are concerned about wake wide. So as far as I can tell, wake wide is like at least on a large Intel system like you have. Wake wide is a no-op. It always returns 0 because it is based on the square of the number of cores on the socket. And so the only way it could return not 0 is if you have 48 squared threads that have been forked on your machine, which is very unlikely.
Yeah, so so I have to admit I still have trouble fully understand this heuristic, the wake wide thing.
Yes, definitely.
So my understanding is because the wake and the wiki is kind of not related. So they actually not related. So did the multiple wiki actually just switch? You have the multiple tasks cannot switch on this CPU. So it's not actually. I don't know.
I completely understand your point that the heuristic is not appropriate, but I don't think the heuristic has any influence on anything on a machine with your configuration. I think the heuristic on every single app, I mean, maybe it's an exaggeration, maybe someone else has some other kinds of applications that have a different behavior, but I think the result of wake wide on every single application on your machine is going to be 0.
Well, I think that's not true. That's the point.
Okay,
it's
fine.
not 0.
Well, it is in his case, and it is, I mean.
No, we're doing lots of wake wides all over the place.
Sorry, what? I missed that.
The problem is that the waker statistics are being calculated between processes that aren't related because you got there because of an interrupt. And the theory is that all of those whacked out statistics is causing the issue.
But do you think the statistics are ever going to get up to 2,500 between the waker and the wakey?
Well, I'll let Lebo step in, right? But you're seeing this all the time, right, Lebo? So it's not returning.
Yeah, I just well, one reason is you have this so they use the number in the LC schedule domain as the factor, right?
Yeah.
So the factor is actually quite big. So I think on the Intel chip, each socket has 48 CPU, right? The 24 cores. So that number is pretty big. So because the wiki flip and the wiki flip. The wiki for wiki and wiki has similar numbers, so they never got the point they should do wake wide. So So that's the, well, again, like I'm just not fully understand the reasoning behind this heuristic. So yeah, it's normally yeah. So yeah, so I so I think we should come up with something better. So something yeah, easier to understand, something like kind of makes sense, right? Yeah. Yeah, to answer, I don't know why it doesn't return 1, why it returns 0, why like we can get similar Wiki flips numbers. So, but the result is getting, it's almost always return 0. That means they always do the Wiki thing. So yeah.
I think it always returns 0.
Oh, it's always return 0.
I think so.
No,
Because the numbers have to be so huge for it to be anything other than 0, and the numbers are degrading over time. So
yeah. But no, on the very heavy loaded system, you will see occasionally it return 1. So that's because I put a trace there and I saw, oh, it sometimes it does return 1, but most of the time it just returns 0. So it's only some very weird case. Yeah.
But I think the problem is something else. I mean, if the heuristic almost always returns 0, then the problem is something else.
Well, it could be also be the heuristic. Yeah. Dietmar, do you want to ask? We cannot hear your audio. Yeah. Okay. Next, please.
I just have a comment, and that is that maintaining this code is a waste of time. And that's because fundamentally the number of times you've had to use the word heuristic, right? I mean, heuristics are going to work for some things and not work for other things. And depending on what you measure, it's going to be good or bad. And so your outcome's going to be random based on what you measure. What we really need to do is the hard work of plumbing the system such that we actually have real hints for what we want the system to do, so that the scheduler doesn't have to guess with a heuristic.
That's
so
true.
We could spend the next 20 years working on this and we'll never get it right. We really have to just
I totally
rewrite it.
Yeah, I totally agree with you. That's what I really want. We want something. Yeah, we want to rewrite this thing. We want to look at the big picture, right? What we're trying to accomplish during wake up, right?
Sorry, my audio wasn't working. I just wanted to add something. We also played with this wake wide recently, and yeah, we saw this function returning 1 or 0, but there's more to it. When you look in select task run queue fair, and you go to the for each domain over the temp shed domain structure, then your shed domain has to have the SD balance flag set to essentially make a difference. So and the difference is not to go into the fast path, which would be select idle sibling, but choose the find idle CPU path for wake ups. So because the topology is normally by default set up with this SD balance wake flag equals 0.
Right.
That means even if your wake wide thing will return 1, you always do the select idle sibling, the fast path. So I don't know where, you need both things to see a difference in the wake up strategy.
Well, actually, so you said,
but I don't think it's a wake up problem. The problem is completely somewhere else. It's how the networking cards work and how the network stack looks like. So unless you can get so there are also networking cards which actually allow you proper filtering to the incoming queue, so you actually can move the interrupts to other nodes if you have enough queues. So similar to what the block multi-queue does. If you look at block multi-queue, that's perfectly fine because you issue it on CPU X and the completion and stuff comes back on CPU X and not on some random other CPU. So networking is a different beast because you do the TX on CPU 10 and the incoming packet comes in on CPU 5. Unless you have really hardware filtering, and that's where you want to go, because anything else you try to do is bound to fail. It's not going to work. It can't. It's heuristics. And heuristics might work for one workload, but they can't work for the other. So this is a whack-a-mole game. It's totally totally bonkers to actually think about fixing this in the scheduler, because the underlying issue is that there's no relation between the TX and the RX, or the connect, or let's say the connection. But hardware filtering in the network card can actually do that, and there are cards which provide that, and there you can fix your problem, not in the scheduler. That's just futile.
Oh, okay, that's interesting. Okay. Okay. I think. Yeah, we can talk about this, Thomas, like offline. Yeah, I probably have more questions to ask you. Anyway.
Sure.
Yes. So, any more questions?
Yeah, it sounds to me like the algorithm is wrong, and the algorithm is wrong because we're just not passing information to the scheduler where we're doing the wake up of whether this should be considered a related process wake up or not. That's just not something that we can do from the when we call wake up. So if we fix that, maybe this problem will get easier.
Exactly. Exactly. Just like
Cool.
what Thomas said, the heuristics are bound to fail. It's designed to fail.
Okay. 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 Sounds good. I think that's awesome. Very good discussion. Yeah. We can go from there. Okay. I think time is up.
Libo, you still have the next talk.
Yeah.
So let me get that set up. But while we do that, it looks like the chat's working again. I cannot seem to get it working through the integrated bit, but if you would go to the matrix link that James sent last night to all of you, it seems to be working there. And hopefully we can have a discussion like we had last year in the chat.
Ooh. Okay, yeah, looks like the check is working.
Right. Live on the bottom left, there's a plus button that should allow you to choose your slides.
Yeah. Okay. Okay, that would be my. Should I get started right now? I just like wait.
Ken, unless you have a question, do you mind turning off your camera?
Okay. Okay, let's. Do you want to take a break? I just like I would just continue to the second time.
Continue. We have a schedule.
Sorry.
Please continue.
Okay. Okay, so the second one is it's about using the LLC schedule domain wake up pass. So it's somewhat related to my previous topic. So I want to talk about like so first is the MDZ. So I think this gets mentioned last LPC by Xi Wang. So basically the new AMD Zen architecture has much smaller LLC schedule domain. Right, so because I have this CCX thing, right? So Zen 2 only have 4 cores, like Zen 3 have 8 core, a little bit better. Well, so each CCX is only LC cache. So basically, it's a Newman node, right? And it's essentially LLC schedule domain, right? So the porting issue we see from last discussion will be more severe. So assuming we fix that. But still, for wake ups, it just have much less space to spread out load, right? So, because in a select idle sibling, right, it will try to kind of do some smart thing like spread out like loads within the LLC schedule, right? So you basically have less space. So think about in an AMD system, you have a 2 CPU, right? Basically, you are choosing between 2 LLC schedule domain. So you can have those 2 LLC schedule domain complete full, and the rest of schedule domain just complete idle, right? So there's a possibility that could happen. So that's just not ideal. So that's AMD Zen. So the second is the ARM. So we noticed that in some ARM system, there's just no LLC schedule domain. So why? Because first, the ARM doesn't support hyper threading. So that means no SMT scale domain, right? So some of the chips don't expose the L3 cache, also called SLC. So I think the L3 and SLC is kind of a little bit different. The SLC is more close to the memory, I think, but I don't know the exact detail. So with that, the consequence is there's no MC domain, right? So if the kernel doesn't say SMT and MC, it just can't have like a doesn't have like any LLC scale domain. So how does that affect the wake up, right? So the wake wide will like using the size of LLC scale domain as the factor. So if there's no LLC scale domain, then the size of LLC scale domain is 0. So what happens is, so if you look at the code, if it's a 0, it's just always between 1, no matter what, right? That means always wake Y. So there's absolutely no wake find at all. Okay, so this like that's wake Y. So the other is this like either sibling. They also look at it for this LLC scale domain, then try to spread the task within a scale domain. So there's a no. So so those two together cause the SCFS wake up just always place the task back to the CPU it was on. So it's always doing that. So no matter what kind of workload, no matter what kind of situation in the system, you could have like the previous CPU may be completely saturated, and it just never put back. So it's not catastrophic, by the way, because you still have a periodic load balancing and other load balancing kind of balance it out. So, but it's just like all the stuff we have in the wake up, like a Slack task run queue fair, just didn't mean anything, right? Just a completely dumb like wake up. So the question is this something we want, right? So again, I just want to bring up the question because I think it also bring up like last year. So like, should we use the LC scale domain the way we're using right now? So right, again, so if we fix the polling issue, still the LC scale domain is very small, right? Small to work with, and for ARM chips, it's always back to the previous serial, right? So can we do better, right? So I try to raise this question because I think there's more innovation in architecture, so you can get all kind of weirdness. So I think we want to accommodate this. Yeah. Please go ahead, ask a question.
For the ARM things, is it really so? Is it that they don't have cache or that they don't share the topology?
They don't share the topology. They do have the SLC. It's hide from us, from the kernel.
I would say just populate this in this case. That's the best way to fix the problem. If we don't know if there is a cache, and right now the assumption is that we can make some fast migration between CPU that are sharing cache because it's not really costly, and we prevent to do that at wake up between two different cache level, between two different cache. So I would say it's normal. If you say to the scheduler, we don't share any cache, at wake up, we will not try to migrate somewhere else, and we will rely on the load balance to do so, right. To have a more I would say clever or smarter load balancing. So right. for the ARM part, just share that there is a cache. Then for the AMD, that the same that you are seeing that so there is only the cache shared between some core, but what's the performance for migrating task between inside this node? That's probably something that we could take into account.
The performance with
the point is that right now in the scheduler, we are defining several levels. One is that we are sharing some, the first one for SMT is that we are sharing some hardware resources. So we try to not back task on the same core in order to not conflict for the hardware resources. The other part is that we migrate quickly when we have this kind of shared package resources, which is mainly we are aligning that with the cache level. It's to say we can quickly migrate tasks between CPU which are sharing these package resources, because the impact will be minimal. And then if they are not sharing anything, we are considering that it's costly to migrate that at wake up.
Yeah.
So I would say if it's not costly because of new mechanism, I don't know, maybe now their C6 is fast enough that we can consider that as the last level of not cache, but shared package resources. Maybe that would be good to mention that.
Well, whoa, that's so sorry. Yeah, I heard the latency across this axis is pretty bad. So I don't know if I mean, it's probably not a good idea right now. But I don't know. Yeah. Thank you, Vincent.
Hi, on the AMD thing, I did evaluate what spilling over from the LLC looks like on Zen 3. I pushed the prototype branch to my Git tree on git.kernel.org. It has node locality, and hopefully you'd be able to find it. I found that what I did was that it searches the local LLC first, and if it doesn't have the LLC, then it calculates what the node mask looks like, but takes the LLC out and then continues to search there to a limited depth. It worked reasonably well for some workloads. I'm looking at the results now. Tbench was a bit all over the place. It was fine for like low thread counts and then slow on higher counts. Hackbench falls apart. Basically, anything that looks overload, the increased search depth just ended up costing too much. Now, there's a couple of things around this. The idea is still fundamentally good, or at least I think it is, but there's other things that need to be addressed first, which means I deferred it. One, it is Zen 3 specific. While Zen 3 is known to have fairly fast communication to other LLCs on the same local node, it's not true universally. So in the prototype, it actually only runs this if it detects that it's running on a Zen 3 processor, and otherwise, no. But other things that I found, our overload detection is a bit poor. One major factor is due to the wake-up granularity, where Hackbench tasks get preempted too quickly, and it fails to make sufficient progress. I posted a series on this about an hour and a half ago, so it's fairly new, and I imagine no one has seen it yet. Depending on how that goes, then it becomes the select idle sibling issue on limiting the depth it searches. That's a topic for later on today, I believe, but it still hasn't been fully decided what to do there. At the time that I was looking at the Zen 3 specific issue, I came of the opinion that both of those problems should be solved first before wedging a Zen 3 specific a search in there. I thought it'd be premature, and the fact that it showed regressions for some workloads because I was getting the search depth wrong, I felt that needed to be fixed first. But the idea is a solid one. It does make an awful lot of sense, particularly on Zen 3. It's just not the first problem to solve. It should be deferred slightly until the wake-up granularity and the select idle sibling discussions get finalized in some way, shape, or form.
Sounds fair. Yeah. Thanks.
But feel free to look at the prototype patch if you like. It's old, but it should rebase fairly easily.
Awesome. I will take a look at it for sure. Yeah. Thanks.
On the ARM thing, I don't really have a strong opinion. Virtualization, it's the same issue though. There's no topology exposed, and theoretically has the same type of problem.
Yeah.
Like, to be honest, I would think if there is no cache information available at all, just fake an LLC and just say it's a socket and just guess that maybe the socket shares resources of some description. It would allow at least for wake wide to work and select idle sibling to at least make decisions on a memory locality basis and just see what falls out. but otherwise I don't have strong opinions, largely because I don't work a whole pile in ARM and I don't work a whole pile in virtualization. I know the problem theoretically exists, but you haven't chased it down.
Yeah. We would definitely need to do more testing. Yeah, look at because we noticed that actually having no LLC SCAD domain, it actually work fairly well for certain workload. But I assume it's probably not work well for other workloads. So yeah.
I imagine it doesn't work well with workloads that really don't want to migrate and want to be left alone as long as possible, like heavily throughput orientated tasks and nevertheless communicating.
Yeah.
There are some oddities around Noom as well, where sometimes it's better to have them split apart, having two related tasks spread apart for memory bandwidth reason, but there's no good way of detecting that from a scheduler context.
Yeah, totally. We don't have that kind of information. Yeah, for sure.
Okay.
Oh,
thank you.
Up. Yep. Thanks, man. Okay, 5 minutes warning.
Hey, Libo, this is Gautam. We are seeing the same problem on power systems as well, especially on Power 10, where the LLC is just one SMT core. It's an SMT4 core. So the problem is compounded by the fact that if we end up, first of all, the search domain is very small and you end up making the task on the same core, you lose out on the single thread performance while there's a sibling core that's idle. So there is an opportunity cost that we're missing out on. We did explore trying to fake an LLC domain at a higher level, like at an MC level, where we try to put that LLC stack, even though the cores there do not share L2. What we found out was for both Hackbench as well as Tbench, at lower utilizations, the results are pretty good because they'll be able to exploit the single thread performance and the wake up is faster. But as the utilization goes up, I think the cache thing comes into play, and we see that we are unnecessarily searching over a large space and not really finding either an idle core or an idle CPU. So at a higher utilization, that those patches were not really having impact.
Yeah, that's kind of what I'm worried about as well. Yeah, that's the searching cost is a problem. Yeah. That's a good point. Yeah. I don't have a good solution for that. I think we need to discuss, talk about this and do more testing. Right. Thanks.
Yeah, I've seen a discussion regarding IBM Power 10, and I think maybe on IBM Power 10 the problem is LLC domain is too small. So when we select the idle CPU, we can only get 4, or on AMD Gen we can only get up to 8. But sometimes what I have seen is LLC could be too large. For example, on ARM, sometimes all the sockets just show one not lowercase. Maybe you have 32 or 40 or 64 CPUs showing just the LLC domain, and sometimes the sage prop doesn't throttle well. So in select idle CPU, we will scan a lot of CPU, but they are not idle, so we waste a lot of time. So sometimes LLC domain is too small, and sometimes the domain is too large. So yeah, we definitely need to figure out how to actually.
Yeah, I think we have the low information for each domain. So I guess we can check we can check the low information and decide, okay, if it's too overloaded, let's just the search costs are too high. The low is too high, then let's have a close range search rather than just go. Thanks.
So the idea, I mean, that I think Shrikar is going to present it in the next session as well, where we want to see if there is a fallback search domain, right, and which can be defined apart from LLC. The first level search should be in LLC, but subsequently, if we can expand that a bit, like a fallback, that is something that we want to explore, at least for power.
Yep. That's a good idea. That's a good idea. Nice. We have a lot of good ideas. So yeah.
Thanks.
I think
Yeah.
what you're hearing is that the LLC is not a universal concept, and therefore it's really not a universal tool for this decision, right? We need something more abstract.
Yes. I totally agree. Yeah. Awesome. So okay. So any more question? I think that we're in pretty good shape. Okay, time is out. So thank you everybody for the discussion and listen to my presentation. So I'll mute myself.
Looks like people are starting to return. Barry, are you around?
Yes.
Okay, I'm going to give you presenter.
Maybe I can start from Aubrey. The first one is for Aubrey.
Oh, for Aubrey, okay.
So yeah, Daval, Aubrey said me that she was not able to connect.
Oh.
To the conf. So I think that Tim is there. So she proposed either Tim to present the result instead of her, or me if Tim can do that. So let's see if Tim is there.
Tim is there.
Yeah, but he's on. Yeah, Tim is there. So okay. So maybe he can present the slide for Aubrey in this case.
So
okay.
Barry, I'm going to give you presenter mode so you can move the slides. And then whoever has to speak for those slides, they can come on and speak.
Okay. Yeah. Well, I'm present.
Okay.
Oh, yeah. Yes, I can move. Yeah.
So
yeah,
our next talk is challenge of selecting an idle CPU, which has a few speakers. I think it's Barry, Aubrey, Shrikar, and Vincent. Barry,
Yeah, exactly. So the goal is mainly to make a sum up of the various proposals that have been done around select idle CPU, and then discuss what would be the next step.
Okay. Should I go ahead?
Yes.
Yes.
Yeah. So I think this is mostly Aubrey's work, and so what we have noticed is that the select idle CPU path does not scale very well, and we use netperf workloads and try to experiment, and we instrument the select idle CPU path and see what happens. So so inside the select idle CPU path, there's supposed to be some throttling of the number of idle cores that's being scanned, but we found that most of the times that path was we did not actually hit that, and then put a throttle on the number of CPUs to scan. And so if we look at the number of CPUs being scanned, most of the time it go ahead and scans the entire LLCs and scan all the CPUs. And it's okay for when the system is mostly idle, it's not very heavily loaded, but things does not work very well if your system is quite busy and you spend a lot of time scanning the CPUs without actually finding and idle CPU. So the idle CPU scan throttles does not work very well. That's like one thing we noticed. Yeah. Okay, I think maybe go to the next one. Yeah, so this was the other work that Aubrey did was to try to find a way to see if we can scan the CPU faster by doing idle CPU mask. So we actually track the CPUs that are idle. So when you scan for idle CPUs, you only look for CPUs in this idle CPU mask. This has its own problems. We find that the scan efficiency improved but the performance is not a universal win. Say for some workloads, it works well, but for others, it doesn't. I think it is mostly due to the overheads of the idle CPU mask update itself, and also it's a lot of cache bouncings of the idle CPU mask. So it's still kind of a mixed bag with this approach. Yeah. So that's kind of the two outcomes that we noticed. Mm-hmm.
Yeah, thanks, Tim. And I think maybe another reason is sometimes the bit mask is not accurate because we are right now updating the bit mask in interrupt timer tick. Sometimes the bit mask is not correct, so we still need to scan a lot of CPU.
Yeah.
Yeah, but we need a trade-off because updating this bit mask can be time consuming. So, I mean, if all the CPU are trying to update accurately this bit mask, I mean, I think that's something that Tim has mentioned, is that the bit mask will be the critical resource and all the CPU will fight to get it. So we can't really afford to have one bit mask accurately sync with the idle state of the CPU.
Yeah.
I'm not sure that doesn't scale really well. So that's why Urbrave took this to say that we update it when entering idle. So we make sure to update it when idle, but we are removing it only when we are sure to be busy. So at least this removes all the CPU which are long running tasks and prevents scanning uselessly some busy CPU, and typically when you are overloaded.
Yeah.
But it seems that it's not yet enough. And so from the previous slide, my understanding is that the sysprot, the way we are, so we are. Do I understand that correctly to say that we are not giving up fast enough trying to find an idle CPU?
Correct.
In most of the case.
Yeah, and most of the case that you scans a lot of CPUs. Like most of the case, in fact, you scan the whole LLC domain. That's bad when you are when the system is quite busy. Right? So you do a lot of work and for no gain. Right? Yeah.
Yeah, and okay, and just for me, do you know if it's because we are wasting time? So we are wasting time. We are stealing time on the running task on the CPU, or it's because we are delaying the wake up of the task that wake up, or maybe you don't know. Because when we are searching for an idle core and an idle CPU, two tasks have some penalty. The one which was running on the CPU, it's just preempted looking for a CPU for the other task, and the task that wake up will be delayed until we found that. That would be interesting to know if it's the running task that is on the local CPU that get some penalty, or if it's the waking task because we delayed the wake up.
We may need to actually do some instrumentation too. Yeah.
Yeah, no, it was just in case you had the information.
It's both, right? It's both.
Okay.
It's got to be both. The real question, quick question, Tim, is, how many cycles are we really spending on this? I know this looks bad on a graph, but I mean, you sort of have to compare it to something. Do you know what I mean? Like how important it is that we're spending this much time doing this. Is it noticeable?
For the micro workloads that we are playing around, say things like hack bench, T bench. Actually, this will be a very significant portion because most of the times there's the work that you're doing is very little, right? So most of the time you spend is actually trying to wake up the other task, and then the other task will run very quickly and then goes to sleep. Yeah, so I would say that the problem is a little bit worse for these kind of micro workload that we usually try to evaluate our scheduler on. But maybe not as bad for like real workload where you actually run for a while and not go to sleep right away. Yeah.
With real workloads, we've actually found that both web surfing and Memcache style workloads are extremely sensitive to the wake-up latency of tasks, where you can sometimes get way over more than 1% performance difference for the real-world workload just by tweaking the stuff in around select idle sibling.
Hmm.
Yeah, I guess we still have some more slides. Maybe we can move ahead and continue discuss after we finish the presentation.
Yeah.
Okay. And the issue I've seen is actually LLC domain maybe doesn't always work for some topologies like ARM or even Power 10. For example, for ARM, for Kempon 920, we have 32 or 24 CPUs sharing the last level cache, and they are exactly one NUMA load. And inside the last level cache domain, we have cluster like 4 CPU will be a cluster, and actually X 86 Jackswell also have the same issue. For example, Jackswell has 24 cores, that 4 of them will share 2 caches. So based on the new topology, actually we can do 2 things. The first one is we can add a new schedule domain for the cluster, and then we can do load balance between the clusters. Actually, we have seen a lot of gain on performance for those workloads who like spreading, like spec rate, stream, and the mathematics, matrix, and array operations, and some multiple threads compression and the decompression and some things like that. And the other thing is we can actually change the scanning order. For example, right now we will scan from the target CPU, but maybe we can, for example, scan from the cluster first. Then after we scan the cluster, we continue to scan the last level cache domain. Actually, we had some prototype to do this, and we are seeing a lot of performance improvement for some scenarios like PG bench, T bench, and MySQL. And one experiment, one test we have done is like, for example, if the tasks are pinning one NUMA load, we just scan a cluster, we totally ignore the last level cache. And I have seen a lot of increase for MySQL. For example, I've seen up to 7% TPS increase for MySQL. So it's just a workaround. If Wake and Wiki are sharing the cache, we just retain the target. We ignore the last level cache. But for this prototype, if we run tasks on all of the 4 lumas or even 2 lumas, actually we don't gain performance because what I have seen is actually when Wake and VK are sharing cache, we don't scan the left CPU in the last level cache. I think maybe it's scan too small. For example, I've seen even my circle is quite busy. I can still see one CPU which is totally idle. So maybe because when Wake and VK are sharing cache, I just escape the scanning of the the left CPU in the last level cache, so the idle CPU doesn't get a chance to be scanned. So to me, if tasks are running in just 1 luma, scanning cluster is totally enough, and it gave a lot of performance improvement. But if the task is a lot pinning 1 luma, actually we shouldn't do this. We should scan more. Even Wake and VK are sharing last level case was sharing And the other problem I have seen is exactly Tim and Aubrey have seen. For example, if tasks are pinning 1 luma, if even I totally ignore cluster, but if I limited the scan number to 4, for example, I totally ignore cluster and I scan from target CPU, but I only scan 4 CPU, I can say actually like up to 4 or 5% of performance improvement of my cycle. So I agree, maybe the sys doesn't start very well. It scan too much. Yeah, that's what I've seen. So yeah, actually I have 2 needs. The first one is what's the best way to scan cluster, and then scan the last level case. The second one is I've also seen sys doesn't start well, on my platform. Yes, Sarkar, do you can hear me? Or
Yeah. So on the Power 10, right? We are seeing a similar problem like what Barry Song is saying. But here, instead of a cluster, our LLC itself is very small. So in what happens is the cores that are there in the same hemisphere, they tend to have a faster cache access, in the sense, though they are not sharing the same L2, which is the last level of cache on Power 10. What actually happens is if both of them are having cooperating tasks, then they still give a better performance. However, what happens is because of the current scheduler where we say the workloads have to be spread, let's say if there are 2 threads, then what happens is one thread runs on one hemisphere, the other thread runs on the other hemisphere. Even though if they are cooperating, what happens is the distance between these 2 hemispheres would be pretty high, resulting in a pretty bad performance. So here what we are, one of the challenges that we saw is when we are doing the select idle sibling thing, the first thing that we do is we try to select the core based on the weight of the current CPU compared to the previous CPU, right? So because of which one of the things that I think we are missing is whether there are idle cores in that LLC or not, right? I mean, it may not help with respect to Power 10, but generally what we are doing is, we assume that if there is one, if we are comparing CPUs, then what can happen is, especially if it's a sync workload, then if there is only one thread running on the current CPU, we think we can just run it there because the CPU is going to give away its time to the waking task. However, in latency sensitive workloads, right? Like PV offline or SAP HANA workloads, or like what Rick already mentioned, right? So in those cases, when there is an idle core lying beside, and we still wait for our task to schedule out to run the other task, we are losing latency. So one thing that we were looking out is, can we scan for idle cores? And if we find an idle core, then prefer an idle core instead of trying to choose the cache affinity, because an idle core in a nearby domain is probably much faster and better for a performance than trying to optimize for the cache. So that is one thing that we saw in workloads. However, as Gautam had pointed out in the previous talk, right? The moment we do this, I mean, especially because we, as Vincent has also mentioned, right, we are trying to share the data across a number of CPUs, and because there is a shared data across number of CPUs, and we are trying to update it at every time there is an it becomes idle or busy. So because of that, I think as soon as the workload increases, the number of threads in the workload increases, we are seeing a sudden regression. We are seeing a sudden performance regression. But when we further increase the workload, then the regression tapers out. So what we see is, in the initial, if the workload is low, this idler LLC approach or the fallback LLC approach generally helps. But if the workload stabilizes to a certain degree, it regresses and then it comes back. So that is what we are saying. So typically what we say is, the idler LLC is, in the LLC first try to find if there are idle cores, or if there are, let's say, on a Power 10 like situations where there are SMT4, or Power 9 where there are your LLC can have 8 threads. You also look for the number of idle CPUs in the core also, in the sense, because one core might have just one running task, and the other core might have 2 running tasks, in which case preferring a idler core seems to be giving us better performance. So that is not something that we are considering today. So is that something that we could bank on? This again is basing on some of the heuristics, but and we have heard a few gentlemen saying that, Thomas and Len also saying that, basing on heuristic may not always help in all approaches. But this is one thing that we observed, that preferring a idler core seems to give better performance than waiting for a cache affinity.
Yeah, Vincent?
Yeah, so among the problem that we have seen about which CPU or which core, which LLC we should select, there is another problem with the current implementation of the select idle core, is that, so we are trying to throttle the time that we'll spend on looking for an idle CPU or an idle core if possible. And the current implementation is based on the average idle time of the local CPU. Which doesn't seem, and we expect that to reflect the state, the load state of all the system, but it's hardly reflect that correctly, as we have seen most of the time we are not throttling that all the time spent on looking for a CPU. So my point is that in this search of an idle CPU and CPU or core, should we change the way that we are defining the time that we should spend? Because right now, in fact, when we are looking for CPU, and that's what I mentioned previously, we have 2 tasks which are impacted. The first one is the task that was running on the local CPU. And the other one is the one that we wake up and that have to wait for a CPU to be selected. So I wonder if in this, instead of using this average idle time, we should look at something that reflect a bit more the current state of the local CPU or the running CPU. Typically, if we are if we have a long-running task that wake up, and should we try to spend some time looking for an idle a CPU with some short idle time, or at the opposite, if we have a task which is known to be really small because of its utilization, should we really waste a lot of time trying to find an idle CPU, or just wait, let him on the local CPU and waiting to be scheduled more easily, more quickly? So my point is mainly that we should probably just change and replace this average idle by something else based on the running task and the wake up task statistic, and maybe on the local CPU as well. Don't know.
There's also the issue that idle time spent takes away power budget from other cores, or just compute time from the hyperthread sibling.
I don't know how much time we have before the end of the call. I think we
5
have
minutes.
5
5
minutes.
minutes.
Okay.
I don't think we should take hyperthread sibling state into account. Because we don't know to what degree resources are being shared between the siblings, and we don't know what the workload is doing, and trying to do stuff around that is just going to be a rabbit hole that we'd never get out of. I do agree on the average idle time thing. Just isn't fit for purpose. It has idle cores is too bad of a heuristic, and it returns false. It returns false positives far too often. Now, I did post up or push out a branch that was the last implementation that I had of removing sysprop entirely, using Aubrey's idle CPU mask. The primary problem I ran into is that while it worked well for some workloads, it fell apart completely for others, and sometimes it was very machine specific. So I was never happy enough with it to really try and push it through. But looking at the wake up granularity thing, I do think that we could replace sysprop, or at least evaluate replacing sysprop with defaulting the search for the full size of the LLC, but cut it completely if the number of tasks on the local CPU is above schedule or latency. Otherwise, decrement that counter, not by the CPU you scanned, but by the number of tasks that are currently running on the CPU you're scanning, so that the busier the domain is, the quicker that the search depth gets reduced. And in the event that it's above schedule or latency, we just give up entirely, and we assume that the LLC domain is so overloaded that the search is pointless. But haven't actually got around to evaluating that last idea because it only showed up in the last couple of days. But the removing sysprop and replaced by idle CPU mask, I didn't manage to get that into a shape where it was fit for purpose.
Yeah, so I think that the idle CPU mask will not be enough.
That was the conclusion I reached as well,
Yeah.
which is why I started looking at other things and current ideas.
That probably help in some way, in some case, in some obvious case, but we still have this mid-range where you are not sure about the load and of the system, where we have to find something else. And maybe another thing, because I think that we have, so also based on the previous presentation from Tim, Barry, and Srikar, it seems that we might have some work to do on the topology description as well. Maybe the one that we have right now is not enough. About right now we have only mainly SMT, last level of cache, and all. Should we have a way to better describe some intermediate set? Because it seems that now we have some intermediate set that makes sense in the different state. I don't know, I wonder, but it seems that that might be good instead of trying to fake something or either redefining, I don't know, the meaning of some flag, but it seems that we need some more intermediate step in new architecture.
I'm not opposed to the cluster idea because I think it has numerous applications. Obviously, there's the ARM one that depends on it. Zen 3 potentially the benefits as well, because Zen 3 could say that the cluster is its actual last level cache, and the last level cache it presents to the scheduler is the NUMA nodes. So it search the LLC first and then fall back. So a cluster will be the real level 3 cache. But we'd have to mess around with the naming slightly to make this make sense. But I believe, but don't know, that sometimes Intel CPUs have a core that is more favored than others because it can reach a higher higher turbo boost value. But I don't know that's for an absolute fact. But if it's true, then it would make sense that
true.
Intel. There you go. Then Intel chips potentially could use a cluster as well. And the cluster being your max turbo boost is the first one you should search and then fall back. So, but short, I'm not opposed to clusters. I think that they have an application more than just ARM.
Yeah.
Sorry to run over.
So, yeah, we are running out of time, but maybe we can continue on the chat, on the mailing list.
This is why we have the hack rooms, right? Discussions don't end here; they start.
Yeah, we'll continue in this case in the hack room, but
yeah.
Thank you, Barry, Vincent, Shrikar, and Tim. We're going to just take another quick 5-minute break here.
I see. I should be talking in the shared notes.
Yes, Daniel, you'll be the next speaker. Your audio seems a little far away.
Okay, let me try to boost the level.
Okay, this sounds much better. I don't know what
Oh.
to change.
I just moved the mic slightly. Let me try to boost the level too. What about that? Does that help?
Yes.
Okay. Yeah, just let me know if it goes out again. I can try to tweak it.
No, sounds great.
Okay.
So it looks like people are starting to come back. So Daniel, I'm going to load your slides and make you presenter.
Okay, I think I may have already done that.
No, I have not. Oh, you are also moderators. Yes, you could have done that yourself. Everybody, back from the break, we have Daniel Jordan from Oracle talking about remote charging.
Yeah, so should I get started right now?
Yes.
Okay. All right, yeah, so as Dhaval said, this is remote charging in the CPU controller. I have been working on this problem off and on for probably the past few months and even less often before that, but it's been bouncing around in my head for a while, and I figured it was high time to get the ideas out and see how people generally feel about them. So my main goal for the session is just to describe the problem well enough that people understand why I would like to do this remote charging thing. So the issue is that there are a few different paths in the kernel that where kernel threads become very CPU intensive and they consume a lot of cycles. And they're doing that while they are working on behalf of a C group. And the CPU controller today doesn't have any mechanism to throttle these K threads or make them pay for the time they've spent later on somehow. So the places where this comes up are, there's this newer feature that the kernel got, I think 2 summers ago, June 2020. The kernel got PA data multi-threaded job support, which is currently only used to initialize the struct pages at boot time. On x86, it uses all the CPUs, and it makes quite a difference in kernel boot time on machines with a lot of memory. That was a great first step for the problem, and it was kind of a special case, which is why it was the first step. It happens at boot time before user space is up, before we really care about resource controls. But there are other paths that we would like this functionality for, and all of them can be triggered by a user space task. One of the pieces of feedback I've gotten upstream is that all these extra threads that I start need to be beholden to the limits of the initiating task that starts the job, and of course that includes the CPU controller. So here I am. But I'm not. So that's my primary interest in the problem. But there are other people and other use cases. So in particular, Facebook has put forward a couple of them. I've talked very briefly and a while ago with Tejan and Johannes about this. Async memory reclaim chews up a lot of cycles. And we've got kswapd now that may be reclaiming pages on behalf of the C group. And we also have this patch that Facebook would like to merge that introduces something called cswapd, which does it in an unbound K worker for when a group starts to hit its memory.high limits. And the idea there is we want to account the cycles that these K threads are spending back to the group whose memory is being reclaimed. And similarly, this is also one from Facebook. In NetRx, we spend a lot of time on CPU. And moreover, we spend it when we're pinning what amounts to basically a random victim task. And we want to account the cycles back to the group that the packets are destined for. So there have also been general complaints from Android about this problem. They haven't gotten all that specific about which K threads are doing the consuming. If anyone here knows, I would love to know more about it. But those are the use cases. And one of the things that makes this problem, which has been around for a while, kind of interesting, I guess we should say, is that every use case is a little bit different. And some of the use cases kind of rule out some of the simpler approaches that we could do. So with Reclaim and NetRx, The idea is both of those paths are doing really high priority work. We want the pages back to the system. We want the package to be received and to stop pending this random task. So we can't, or it's undesirable to throttle those kernel threads in real time. What we want instead is to account the time that's spent in doing that work and then somehow pay for it later. And then, NetRx is also kind of a special case in that it has to start accounting the cycles before it knows the group to account to. So, it has to do enough processing of the packets to learn the port and then, the task and then the group. And so another sort of requirement around making this work for all of the problems is being able to support a method that can account before it knows where it's accounting. So, those two things basically rule out some of the more obvious things that have been tried. Basically anything that involves spawning a K-thread directly into a C group, migrating a K-thread into a C group. There's been a little bit of discussion about bouncing the work to a K-thread that's already in a C group, but that's cost prohibitive for things like NetRx that don't run for all that long at a time. So I hope I've gotten across that the requirements all kind of imply that we need some kind of a way for the kernel threads to be accounted outside of the group, which of course leads me into remote charging. So, the high level idea is we want to, save the time that we spend and then push it to the task group to be paid back later somehow. And in my prototyping efforts thus far, I've spent a lot of time on the weight control, not as much on bandwidth, and not at all on uclamp, though not really sure we would want to do that for uclamp, but you tell me. I see remote charging happening in kind of three phases, at least the way that the prototype looks like this week. First, of course, you have to incur the debt when the K-threads are running, and I've got some interfaces that are living in sched/core.c with all the other CPU controller callbacks. And the K-thread can call CPU remote charge begin. You can note the absence of the C group argument to that function so that we can handle the NetRx case where we don't know where we're accounting to yet. And, inside that basically just saves a timestamp. And then, anytime during the time that the kernel threads are running, we can call into CPU remote charge account to push what debt we have incurred so far to the task group so we can start paying for it sooner rather than in a giant mass at the end. And then, of course, when you're done, you call the end variant. I'm accounting debt to both the target task group, wherever that may be in the hierarchy, as well as all of the parents up to, but not including the group. So, that's phase one, just the K-threads incurring the debt. Kind of the second stage of this is, of course, paying the debt. And the mechanism that I'm choosing to do that with right now is increasing the vRuntime of the group entities that are in debt. So when such a group entity is switching off the CPU, input prev entity, I'm increasing the vRuntime to force it to stay off the CPU longer than it would otherwise. Of course, for such a method to be effective, there has to be competition on the CFS run queue, or else it's all pointless. And, I think there's some latitude for implementing some kind of debt forgiveness, but I may be getting way ahead of myself because, that's all in the details. And as I said before, my main goal in this session is really to just get a feel for how people are thinking about this approach. So, those are the first two steps, just incurring the debt in the K-threads and then paying it in the group entities. The third step is that once the vRuntime of the K-threads has been increased, there may be some sort of scheduler event that changes the scenario so that we need to remember the debt that we have paid by increasing the vRuntime, but not yet actually settled by forcing that group entity to stay off the CPU for longer than it would have. So such events might include, the indebted group entity goes off the CPU. Of course, we need to stop then. There's no more competition. Number running falls to 1 on that run queue. Or else the indebted entity itself is switching back on the CPU. So we need to save that extra vRuntime for the next time it goes off. you know, the question naturally arises, like, how do you quantify what debt is unpaid, given that increasing the V runtime is sort of causing an absence of something? You know, the group entity is not running. I've tried to illustrate that with the graphic on the right-hand side here. So this is drawn from the perspective of an indebted group entity. So of course it has a sched slice, and if it's got competition, it's also got time that, at least in the ideal, it's expected to be off the CPU. And if we didn't care about remote charging, we weren't thinking about that at all. The only thing that would happen is the sched period would pass, and again, in an ideal sense, the K thread would get one chance to run within that. But because we've increased the V runtime, now the K thread is forced off the CPU for a little bit longer than it would have. And so what I do is I basically just take a timestamp when the group entity switches off, and then I take another one whenever one of these scheduler events on the left happens, and see if I've gotten outside of the off CPU time yet. And if so, I can quantify how much debt has been paid, if any, and balance the books. So that's sort of a quick run through of the high level approach. And I do have more things to say in the next slide, but I think I'm going to pause right now and just open it up for anyone to give any initial reactions to this thing that I've just described.
A quick question: is it always possible to find the correct C group to charge? For example, say I think you mentioned the page reclaim using K-swap D, right? So the pages that you are reclaiming may belongs to a C group, say, but actually the reason that you are reclaiming pages from that C group is because some other C group is requesting the memories, right?
Yes.
So yeah, so you, like, if you charge the times to the C group from whom the memory you are reclaiming from, you may actually be charging the wrong person.
I completely understand the point that you're making, and that had also occurred to me. You know, this idea, I think, I can't remember if I heard it from Tejan or Johannes in that thread, but I think one way to think about that is, yes, the decision about which group to account to and reclaim is arbitrary in that way, but it's always proportional to the amount of memory that the group has on the system. At least I think, in the sense that if there's a group that's putting a lot of memory pressure on, that group will get more cycles accounted to it than other groups, if you follow.
So is this a solution searching for a problem? Or do you, I mean, I understand it looks more fair, right? This will be more fair, but is there something actually going wrong because of this that we're trying to fix?
Well, the idea, I mean, is that the kernel threads are escaping the CPU controller. So on a system that's using this feature, you know, this background activity is potentially allowing a group with very strict limits to interfere with other groups in a way that we don't intend. You
But
know,
can you actually demonstrate that? Like, does something actually fail, or is this theoretical?
well, I mean, we're not talking about correctness, really. I mean, maybe correctness of accounting, right? So it's not like, you know, I'm not sure what failure mode that you really mean here. Could you expand on that?
Yeah, so can you show when this is working versus when this is not working, something works better? Yeah, failure is probably too strong a word. I probably, maybe there's a better word, but you know what I mean? Like, what
Okay,
gets
sure.
better?
Yeah. Well, so, I mean, take the weight-based control, say. You've got two groups, A and B, and the weight of A is 10 times that of B, right? And B starts one of these jobs. It's say it's starting a virtual machine and it's on a big server. And so it wants to use a lot of CPUs to pin the pages, and its weight does not entitle it to the amount of CPUs that it is using. And so this feature would help to account the time better in that way. I mean, you can directly observe that the CPU time of both groups will converge more to the ratio of 1 to 10 than they would otherwise in that case.
Okay, so you can measure when you've succeeded.
Yes, the metric that we're looking at is CPU time as expressed through weight and bandwidth. And you go ahead, Double, sorry.
Sorry, I did not follow the protocol correctly. Would it be fair for me to phrase this slightly differently, saying the problem is this extra accounting, or rather this extra free time a user is getting, a cloud provider may not be happy with, and they would like them to get the time that they're actually paying for.
Well, that's true. I mean, especially if you look at it through CFS bandwidth. I mean, they could, in these paths, get more CPU time than they are allowed. So I do see in the SCAD IRC channel a question about why can't we just move the task temporarily. That will absolutely work for PA data, but it will not work for Reclaim or NetRx because we don't want to throttle those in real time. We can't have the threads be throttled when they're doing that kind of high priority work. It's best to pay it later and have tasks that are actually in the group pay for it. All right, well, if there are no more questions, I can say a little bit more about the status. I'm not sure where we are on time. 15 minutes left, I think. I've seen another comment from Peter. I think maybe we could bring that into the talk, but otherwise I can always look later. So the current status is that I do have a prototype that does all three things that I mentioned. It incurs, pays, and saves the debt. And I have done some bare minimum testing to make sure that this is behaving the way that I expect. But there's a lot more to do. And in particular, of course, we need to have some idea of the performance impact. I haven't touched CFS bandwidth yet in the code, and I would need to work on some of the more fine points, but I definitely think that given the comments so far, we need to converge better on to what extent we need to be accounting all of this work and make sure that people have a better understanding of the problem.
Hey, Saravana here. Question, maybe you already kind of taken this into account, but some of the work queues, and I think the K-threads, K-threads are processing work queues. And if you are going to restrict the CPU time a K-thread is getting, subsequent items in the work queue, the system work queue could get delayed in terms of processing, right?
Yes, that's true.
How much of that have you kind of looked into? How is it going to complicate this?
Well, that was actually one of the objections to one of the previous approaches. So if I go back here in the slides, one of the things that I worked on, and I was piggybacking off of a Red Hat engineer named Abandoned DOS, I was trying to make work queues C group aware. And I was actually migrating the workers into the C group at the time that they were running the work. Your question is about, what happens when a K worker is running and being throttled and holding up works that are behind it on the queue. this proposal would avoid that problem by not throttling K workers in real time. It would be just timing the work that they're doing and then pushing that time to the task group to be paid later.
Thank you.
Yeah, no problem. All right, well, the feedback so far is that I think people are maybe still a little bit confused about what the problem is and why this feature might be needed as opposed to other, conceptually simpler ways to do things like migrating threads, moving threads around. If that hunch is right, could somebody maybe ask a question so I could clarify? I feel I've got more details to present, but I don't want to dive too far into those without making sure that everyone is on the same page.
No, I follow you. I thought you clarified well. Probably the way I should have asked my question was, how do you measure success?
I see. Okay. Okay. All right. Well, I'll just get into some of these questions then. And I guess I better bring this up as long as the discussion is not off to a fast start. In my testing thus far, I ran a simple experiment where I'm on a 2 CPU VM and I've got some long running tasks. Those are the blue and the purple. And I'll focus here on the blue, on CPU 0. And then there is another task, the yellow task that's just woken up that is in debt. And the weights of blue and yellow are the same. So what I would expect, in the absence of other factors, is that blue and yellow would get about the same time on the CPU and switch off evenly with each other. And then because yellow is in debt and its V runtime is being increased corresponding to that yellow slice would actually be smaller initially than blues. But what I saw actually was the exact opposite, at least initially. And then as you can see, with more sketch slices passing, eventually we do see yellow slice start to shrink relative to blue. And the behavior I was seeing is actually an existing problem in the scheduler, where the debt was being effective. It was forcing yellow to be off the CPU for longer than it would have been otherwise. But it's because yellow's group entity, the load average in the task group hadn't had a chance to stabilize. And I'm sure that most scheduler folks are aware of the problem that group entities weights are overestimated if they've been idle. So when they come right back on CPU at the beginning, they get an unfair amount of CPU time due to some approximations that we have to do, and I think it's calc shares. So, for tasks that wake up and have to pay debt in short bursts, it is so effective even if it looked otherwise.
Sorry, do you have the wrong behavior of the previous? I mean, my understanding is that what you're showing is the correct behavior. I'm not sure what was wrong and what have been fixed based on your
Yes. There's actually nothing wrong. There's no problem. I was just bringing it up to mention that if just to harp on the existing problem, essentially, that we have this estimation logic that doesn't always work as well as we'd like it.
So, do I am correct? This is a bit out of, not related to what you were mentioning before about accounting some additional runtime. I'm wrong. I'm not sure to catch what I should see there, in fact.
Okay, sure. So the yellow task here has just woken up and it's had debt accounted to it.
Yeah.
So my expectation would be that since the weights of blue and yellow were the same, that yellow and blue would get equal runtime without debt, but because they did have debt, yellow would have less runtime. And that is not the case. And I'm simply pointing out the interference from the overestimated weights of group entities. So there's actually no problem with the debt implementation. It's just sort of an unfortunate side effect of how the scheduler behaves today.
So, okay, it's not related to the previous. Okay, I understand a bit more.
Right.
Yeah, there is some approximation. I mean, it's always, but yeah. Also, I'm a bit surprised about that really depend of the skate period. I mean, I don't know how long you're running, but or how long you're idle. But if you're idle more than the skate period, then in this case, we will just will get more credit compared to others, to the always running task.
Not sure
Okay.
I'm following
No,
your
it's
point.
just that really depends on how long you're idle compared to your skate period, because we are capping all the VRun time. And so I'm not sure if there is a real problem there.
No. I mean, no. It was just a side effect of the experiment. It was just kind of a way to show some of what I'd been thinking about and some of the unexpected things I found along the way. It doesn't involve debt, but there's actually no issue.
Daniel, if I understand it correctly, the plot that you're showing is with your changes, right?
Yes, that's correct.
Okay, I think it might have helped to have a graph that didn't have your changes. I think that's what's throwing people off.
Okay, that's good feedback.
Yeah,
I
nothing.
thought the key up here on the upper right.
Before, yeah.
Oh, I'm sorry. I spoke over you. All right. Okay. So so here are some points for discussion. You know, one of the problems that has come up in this work that I really don't have a good answer for yet is it's not always correct to incur debt. So if the system is sufficiently idle, then there's no reason to be incurring the debt and going to all this trouble of having to pay it back. And yet, CFS generally doesn't have a habit of keeping global statistics of any kind, with some exceptions, and notably the load average in task group. So, you know, this is kind of a meta question of this work is, you know, how much do we really care about balancing the books absolutely correctly? What heuristics might be the right ones? How much trouble are we going to go to? So I had some ideas about trying to collect these metrics, but it's early phase yet, and they may not be worthwhile. Another question about the implementation is where should debt be stored? So when K-threads, you know, save the time and they push it to the task group, I see two options. You could account it in a global bucket in task group, or you could do it locally in the group entity that's going in debt on the CPU that the K-thread happens to be running on. And, you know, clearly there are some obvious upsides and downsides to both. Global is very simple. It mimics CFS bandwidth in a lot of ways, in that you're trying to take a global quantity and distribute it to all of the per CPU components of the group. And it also means that debt won't go stale. It won't get stuck in a local bucket and never be paid in case the group also has some CPU affinity settings that preclude it from ever running on that group entity, or else the system just happens not to schedule on that CPU very often. Conversely, of course, you've got the scalability of the local approach by saving it in sched entity. There's just a little bit more complexity if you're even willing to go there in terms of making sure that, you know, debt doesn't accumulate in a place where it's never used. So, you know, you could imagine pushing up the debt tree so that it's not all concentrated in one CPU. Got a 1 minute warning, and I can't see my slides anymore. I'm not sure. Should I take presenter back? I can just minus it. All right. And then finally, there's some limitations to using the view runtime to pay debt. So, you know, if the task group is not competing with any other entities, then obviously it can never be effective. And I have seen cases in my experiments where the system does happen to schedule groups in silos of CPUs, I suppose you could say, such that, you know, the debt, again, will never be paid. In practice, for real things, I don't think this is a huge problem. I have observed that the scheduler tends to schedule tasks from different groups together on the same CPU often enough that this may not be a real issue, but nevertheless, for things like CPU affinity, it could still be a concern. And, you know, of course, there's also this sort of second order effect where multiple entities that are all in debt might be scheduled together. And in that case, they would all be paying debt against each other, basically to no purpose. So perhaps some additional logic about tracking whether there's at least one entity that's not paying debt might be called for in that case. So that was pretty much all I had to present. Are there any further questions, comments? Okay. Well, thank you.
Thank you very much, Daniel.
Thank you for your attention, guys. Yep, thanks.
We'll be back after the break.
Can you hear me?
Audio okay?
Yes, yours. I can understand you. Can you hear me?
Yep. All good.
Cool. Currently don't know where we get the slides from. I hope that if somebody comes back, do you see somewhere where without slides? I don't think so. Keyboard. I was hoping that there is somebody. Daniel, can you help find our slide?
You're, let me see which slide I placed here. So it is the talk number. What is
the talk number is
or maybe what is the title? It is
per past IO boost tracking number is 221.
Let me see.
Perfect. Yes, and can you give me presenter rights so I can click through the slides?
Yeah.
Okay.
You are.
Okay, this is, and next slide is. Okay, next slide is here.
All good.
Okay, and then I have a pointer device as well. Okay, I think, Beata, we don't have to switch, right? Like for the last slide, I just change to the last slide whenever necessary, and then.
Yep.
Beata, my audio, is this okay, or do you
Yes,
think it's...
it's okay. It's okay. I mean, I can hear you clearly, so
Okay, perfect.
fine.
Yeah, I can hear you guys. Maybe Beata's volume is a little lower compared to Dietmar, but
Maybe I'll
Okay.
try to increase it a bit. Give me a sec.
if we can, that would be nice. It would be in an even volume. Otherwise, like kind of Dietmar is louder than you.
Is it anyhow better now?
No, it's worse, I guess.
Not really. It's the same.
Oh.
I can understand you, but it's a little bit low.
Yeah.
Okay, just trying to switch. Is it better now? No?
Yeah, at least I think it's better, but I'm not sure if it's because you're kind of closer or if you change the settings.
I did
People
change
are complaining that I'm too loud, so I turned it down more.
Okay, so it looks like people are back. Our next talks by Beata and Dietmar. Guys, go ahead, take over.
Okay, thanks. Hi, I'm Dietmar. I hope my mic is not too loud now. Beata and I, we work in the ARM kernel team, and we would like to present or discuss her ongoing work on per task IO boosting. Since she was on holiday, I prepared some slides, and that's why I will do the short presentation at the beginning. So let's first recap what IO Boost is. The picture on the right-hand side is from a discussion between Joel and Peter from 2017, in which Peter explained how CPU frequency can affect IO performance. Just to summarize, the boost helps the IO weight-bound task that has usually a low utilization and hence would choose a lower CPU frequency by itself. The boost simply lets the IO cycle time decrease and the throughput of the IO operation increase. Current design. Currently, IO Boost is implemented within schedutil governor. It's a per CPU mechanism. Boost can be built up by CFS task in IO wait during their enqueue. There are 4 discrete boost values covering the CPU capacity and utilization range between 128 and 1024. 0 would mean no boost. On the right-hand side, you see a block diagram illustrating how the boost can be built up, maintained, and reduced, or even resetted. Without going into the details here, we have to deal with the Sugov rate limit, which is a default value of 10 milliseconds. We have systems specifically in the ARM world sharing CPUs and CPU policy, CPU freak policy. And obviously we have to deal with a tick value, which is used to reset the boost. All of those things have an influence on whether the boost is increased, decreased, or maintained. And Sugov uses the max out of the natural CPU utilization and the boosting when it asks the hardware to set the new frequency. What are the issues with the current design? First of all, even though the boost has to ramp up over time, there can be still sporadic frequency spikes. That's because since it's a per CPU implementation, unrelated tasks can build up the boost. Issue number 2 is specifically for IO devices which have a long response time, and that can hinder to build up the boost. Specifically when on ARM devices, when the tick is only 100 milliseconds. Third issue, we can see this on our devices where we have to deal with shared policies. The frequency setting for a CPU B, for instance, can reset the boost value which was built up on CPU A, even though the Sugov data is completely per CPU. The last 3 issues here on the slides, that task migration should follow the task migration should lead to also boost migration. The task uclamp should be able to cap task boost values, and finally, that boost should be taken into consideration for task placement on big little systems. It's not addressed by the current design. So the new design proposal is to move I/O boosting from the governor into a per task mechanism. We track two signals. First one is the time being blocked on I/O, which we therefore call sleep time. And the second one is between wake-ups of an I/O task. And this is what we call I/O sleep time plus runnable time. Only those two signals allow us to discover I/O wait pattern, which we call modes, and then to map them into task boost levels, similar to the one we already see in SUGOF. The wait signal, it means the first signal is essentially sufficient to discover the tendency of the boost signal. That means whether it has to be increased, maintained, or reduced. This is done by comparing the delta, that means the current and the previous sleep time value, with a margin. And we distinguish three different modes here: increase, maintain, and reduce the boost. So when we deal with reduced boost mode, this will automatically translate into the action to actually reduce the boost of the task. The second signal I mentioned before, sleep plus runnable time, is used in the other two modes, which are increase and maintain. For an example, if we are in increase mode and we figure out that the task was mainly sleeping, that means more than 75%, which is another margin, of the second signal, sleep plus runnable, then we wouldn't actually further boost the task, because we simply think it's not worth to do it because it's running for such a small amount of time. To summarize what's on this slide is we think that we need both signals, not only the sleeping signal, to set the boost level for a task, and therefore to be able not only to respect the performance requirements of this task, but also the orthogonal requirement of the energy consumption. On this slide, you see an example of what I just was talking about. This shows a simplified presentation of an IO-bound task with its activation and sleep time phases. We start here. The task wakes up from I/O, and in this moment we would set the task boost mode into an increase mode. That means we would essentially set an initial boost value after the value was 0. Then we detect that the I/O sleep time reduces more than a certain margin, and that means we can conclude from this that the boost is actually working, and we would increase the boost further till we reach a moment where the runnable time and the sleep time are stable, and this is where we would switch into maintain boost mode. The boost mode dictates boost levels. For instance, if we are in increase mode and the task is running more than 25% of its sleep and runnable time, then we would increment the boost level by 1. Obviously, having this information per task is good, but for frequency driving, we do need some kind of per CPU or per run queue aggregation. And currently, this is implemented as max aggregation when such an I/O wait task is enqueued. This per run queue boost level, has to be implemented also as a signal to be able, A, to retain the boost level on a run queue when the task with the highest demand goes into another I/O sleep cycle, or B, when we want to set the boost level to 0, or consider another I/O wait task on this run queue, then the highest boost level, when the highest task when the task with the highest boost level migrates. So before I hand over to Beata for the discussion part of this presentation, are there any questions regarding the contents of the slides so far? Seems not to be the case, so we switch.
Maybe Beata will cover this, but we talked about some coin toss and playing with the margins and whatnot. I was wondering.
Yeah, I think this is our first discussion point. I just described briefly, we do need some margin to set the boost mode between increase, maintain, or reduce. And the coin tossing is essentially applying heuristics when it comes to compare the sleeping time and the sleeping plus runnable time.
That's correct. Dietmar, thank you very much for this presentation. I might be still in a holiday mode, so please bear with me. I hope you all can hear me properly. As for the margins and the coin tossing, the proposed solution is making some assumptions on how the sleep mode and how the runnable time is going to play out, and whether we're going to see some patterns in it or not. Coin tossing, it's heuristic. So the heuristic did show up on today's conference already. So it will work on certain cases. It will not fit for others. So that's why the coin tossing, we're trying to make the best decision out of the data that we have. But we also need to consider the possibility that the decision will not be the perfect one for each possible use. Margins are there to control the boosting. If we are moving the boosting from SUGO, which is the per CPU feature, and we are moving this to be a per task feature, we are losing some of the options that SUGO is using to constrain the boosting and keep the boosting value in line. So we are losing all the timing aspects that SUGO is using. So the tick and the rate limiting, we don't have that when we move to the per task boosting. So the margins are there to make a kind of as sane as possible decision on whether we should maintain the boost, reduce it, or boost even further. So what we've been experimenting with so far is predefined margins that have been selected based on the ability to make a quick calculations. But the margins were telling us whether we are seeing a significant increase or decrease in the reported time for either sleeping while waiting for the IO request to be completed. And the same goes for the runnable time. So those margins are telling us if it's a significant change or the change is small enough that it doesn't really make an effect on the overall performance and energy consumption. So this is where the margins come into play. If that's clear enough.
Okay. No, yeah, no, I understand. Yeah, got it. So I have actually I kind of gone through slides and a bunch of questions on it. One other thing is actually a more fundamental question for me to understand itself. When you're talking about I/O boosting, I was kind of looking at the upstream kernel code. The number of locations where I/O schedule is called is not that high. So what are we considering as I/O wait? At least from a common perspective. The reason I'm asking this is, for example, if we're trying to render a frame and you send something to GPU and waiting for it to come back, are we going to consider that as I/O wait or no?
Possibly, yes. I don't think that's in all the cases, but yes, the I/O wait is being triggered whenever the I/O schedule is being called within the scheduler. That's going to be mainly block devices, file systems, NFS, and related things. So
Okay.
it's kind of like a broad scope of use cases.
Is this kind of applying for networking use cases too? If you're trying to do packet transmission, is that something that's considered IO weight or no?
No, I mean, in case of networking, that's going to be with the NFS, which is just file system over the network, right? So it falls down under the file system one.
Yeah, no, I was thinking more in terms of just like say download upload speeds. One of the issues we've seen before in other products is it benefits to run the CPU faster when you're trying to do transmission, receive, and transmit, and that's going to affect your upload download speed because you're trying to send packets and the network card is waiting for you, or trying to receive packets and it's waiting for you.
Mm-hmm.
That's one case where it helps. So just kind of trying to understand if you're trying to solve those kind of problems too. If you're not, that's okay, but it's kind of curious.
Honestly, I haven't checked how it plays with the networking stuff, so I can't really definitely say whether that's gonna help or not. That depends on how the networking work is being scheduled.
Okay. Another thing, unless somebody else wants to talk, please turn on your camera and I'll give some more. I'll stop talking. Another thing I had in mind was similar to networking. This is like a general theme of problems that need to be solved. Maybe IO boosting is not the way to solve it. That's okay. But say you're having two devices in a producer-consumer fashion. GPUs is an easy example to kind of pick. And you need to run them both CPU and GPU at different frequencies to get the performance you need. But there are multiple combinations of their frequencies that would give the same performance but have different power impact. That's something that would be good to solve from a community perspective. I've been thinking about it and been playing around with some of the stuff that's kind of very different from what you're doing. That's why I'm asking about it, but it's too early to kind of share anything useful. But that's an open-ended problem that needs to be solved.
Yeah, so the solution we are proposing, or we are trying to kind of describe on this presentation is we are aiming to increase performance, but we also want to save the energy. And because we are making decisions on the boosting level, so how much we are going to boost and thus influence the frequency increase, that is based on what kind of behavior we are seeing with regards to the IO block time and the runnable time, because we are comparing the two. So the whole mechanism is kind of dynamic, and it is supposed to adapt to the workload changes. So you're going to see increases of the boost level or decrease of the boost level depending on how the timing plays there. And we also are trying to find the point when boosting doesn't really reduce the time spent while being blocked on the IO request. We are assuming that at some point, even if you reduce the time spent on the CPU, it doesn't really help the device. So we're assuming that at certain point, the device is possibly running on its high performance level. So we don't want to boost even further. This is for the cases when they share the same power or thermal domain. So it is supposed to be dynamically adapting to this case. So if you have a CPU and GPU, and then we see that the time spent on the GPU doesn't change much, despite us boosting the frequency, we will stop boosting because we don't see much point of going even further. It will also try to reduce the boost if it sees no changes in the timings, assuming that we might have chosen too high boost level for a given workload. So it will still try to adapt to whatever it's being reported.
I have some responses, but I want to let other people talk, so I'm gonna.
Hi, I was just going to add to this question. So there is more than GPU device. We would like to see some other mechanisms like the interconnect, where they are actually pinned to some, in our case, big CPUs. When you increase the frequency, you actually increase the frequency also of the internal buses, which also affects your I/O to the storage, such as UFS. But this is not addressable in a straight way because the interconnect framework is kind of a static, and it makes some assumptions. But the major goal here is just to have a working proof of concept to increase the frequency of the CPUs, and then maybe think about more of those related devices, such as buses or GPUs or another
So
stuff.
this is kind of problematic from that point of view that the scheduler doesn't have any information regarding which device is actually performing the IO request. So I don't think we want to bring that information into the scheduler's world. So all we can do is try to make some kind of decisions based on the response time. I don't think we need to make you aware of how we can change the frequencies for the devices that are serving the IO requests. At least that's my opinion.
I agree the interconnect is a different problem. Yeah.
In your proposal, I don't see anything related to the current frequency of the CPU, which impact the running time. I mean, we have tried to make the scheduler and everything frequency invariant, which means that the value that you have doesn't depend on the current frequency. But that doesn't seem, it seems like you're going back to the fact that you are computing absolute runtime or sleep time, and then you will overestimate the running time at low latency, at low frequency, which will, you will bump the frequency too much, then go down and up. That seems to be a bit, that would be good to prevent this kind of ping pong.
Yes, that's one of the things we want to address. That goes down to which clock we are using to get the timings for the sleep time. So that remains an open issue on our side. But yes, that's a fair point, and this will affect the timings calculated here. Yeah.
Was this a remark related to build up those signals based on the PELT infrastructure we already have, using the PELT clock, or?
It's just that, yeah, we have this PELT clock. I wonder, I haven't looked in detail, but the waiting time on the CPU, I wonder if we can not just sum up this kind of the PELT signal of the running time and some IO waiting time. And that will just scale and give you how much time you are waiting, whatever the frequency. Which means that if you are I don't know, if you're decreasing, I mean, the point is that you could compensate during idle the fact that you're running at a lower time. No, I don't know. Yeah, the point is that I see some kind of, the result that you have will change according to the current frequency. And that's exactly what we have tried to remove everywhere in the scheduler. You have a metric, whatever the frequency, the results stay the same. But, yeah,
that's a fair point. Yeah. That's still something that we need to address. If you were referring to using the runnable signal, if I understood you correctly.
Not especially the runnable. I don't know, because in the runnable you are not always you're not in IO wait. So in runnable you are in queue. But I was wondering if you could use a PELT signal that you can simply sum up with the running time.
In theory,
so you will get.
In theory, yes, that's doable. But then also comes the problem of the cost of using PELT signal. So I guess that we need a little bit more testing on the performance side of the whole solution itself. What to note that this will be placed on the wake up path. So we need a little bit more experiments to see whether having a simplified signal versus PELT full-blown signal makes sense from the perspective of the overall performance. But yeah, it's something that might be considered, although we're still aware of the costs of that.
Yeah, this is definitely, I mean, we have to get the signal in schedule, right? And then try to wake up for IO wait task, which is a little bit outside the realm of CFS. But if this is possible to introduce a new PELT signal there, then it also could use the PELT clock.
Actually, I was going to, I wanted to ask a question about exactly the mechanisms, right? Because we've been talking about the policy and when we make frequency changes decisions and stuff like that, but the how we deliver the boosting into the wake up path and into schedule is actually an interesting question. And if I mean, from what you have explained in the slides, I think one of the things you're trying to do is have a signal per task, and then you increase the signal and then aggregate it per run queue, you max aggregate it and everything. And all of that sounds an awful lot like uClamp, for instance.
The max aggregation on the run queue, yes, that's resembling uClamp behavior at this point, yeah.
Yeah, so it just, it's another maybe approach for this would be to basically have something where we say that we could have, kernel-driven uClamp values, and then we would get some kind of governor that would decide when to boost a task and set the uClamp min of a task to a higher value, something like that.
That's an interesting idea. I'll probably have a look at that. Yeah, it might make sense.
I think if you have problems with how to, if you have requests from user space and from the kernel coming in that are, what do you do? But
there still comes the problem of determining and syncing whenever user space and kernel space change the uClamp value. So there might be a little bit of tossing of that. But yeah, that might be interesting. Thanks. As per the decision making and the details. So we are experimenting currently with those two signals which are implemented as EWMAs. The wake up, the sleep time and the IO sleep time being the same way as delay account block IO and the same way as number IO wait are being implemented or decremented for the rank level. So it's plugged in the same places. As per the runnable and sleep time combined as a single signal that's being calculated on the NQ time. So that's time between wake ups from IO. So this is kind of also like a two-stage decision making. So upon registering that the task is going into sleep and then coming out of, is being woken up out of IO, that's the first stage when we try to determine what's happening with the sleep time. So that's the first stage when we are setting the boost mode, whether we are increasing, reducing, or maintaining. And then when we reach the NQ path, it's still only the CFS tasks, by the way. And once we reach the NQ time, we are having the second stage that tries to determine what the runnable time is also changing as well, and if it makes sense to reduce that even further. If that answers your question.
Yes.
It wasn't clear to me if this is already addressed. How is this going to affect task placement? Let's say increased performance is going to help. At some point, if it's a little CPU, it might not be sufficient. You might need to move into a bigger CPU.
Yes. So that's one of the reasons why.
Quick second question is what use case are you using to test if it's helping, whatever you're doing?
Could you repeat the second part, sorry?
What's your use case you're testing against or a benchmark to figure out your changes are actually
right? Okay. So your first question, that's something that Dietmar was mentioning in the part of issues with the current design. So currently with SUGOF, we have no control over the boosting value. So for example, you could completely decide SUGOF has no notion for that. We don't have support for task migration. So task migrating to a different CPU, definitely migrating to a different cluster needs to build up its boost from scratch. And there is no task placement support for boosting IO bound workloads. So having the idea of tracking the boosting per task gives us the ability to fix those 3 points. So the boosting is strictly connected with the task. So whenever task migrates, the boost follows and it stays at the last recorded state. We can easily respect uClamp because the boost levels that we are using, they are resembling the SUGOF boosting, but we are mapping that to the utilization. So it's very easy to clamp the boost level within uClamp minimum and maximum values. And that also can be used on the task placement. So we can.
But currently you're not using it for task placement, right?
Currently, no. But the idea is to plug it in and to use it, yes. So that's what we're trying to achieve. One quick thing before my time runs out. The idea of having per task boosting is not my idea. That has been suggested before by Quantum. Quantum, please correct me if I'm wrong. But I just want to give him the credit that doesn't come from me. As per the testing, we've been testing mostly on the asymmetric CPU capacity systems. I've been using a benchmark like FIO, Sysbench, with the IO benchmarking testing with it. So that's mainly what we've used for testing. We do know that we have a little bit improvement on the performance side. If we have performance upgrade, we still consume more energy, but how much we can tweak that still needs self-testing on setups with different devices and different workload characteristics. And my time is up.
I just want to add a few things just for like that uClamp relationship with the per task. It's just to explain this is required because on Android, for instance, there is a desire to disable this IO weak boost for certain tasks because we don't want them to like consume energy. And just to give the background of why this per task and uClamp relationship is just, we don't want this all the time. We don't want IO weak boost for certain tasks, and that enables us to do that, which we can do today.
Thanks. Thanks, guys. All right, if that.
Thank you, Beata. Thank you, Dietmar.
Thank you, guys. Thank you.
That was a really nice talk. We'll go back to a break and start in another 5 minutes. As usual, I'm going to start a poll. Vincent, you should now have presenter mode.
Yeah, it works. Just checked. Thanks a lot.
Okay. Okay, perfect. It looks like a bunch of folks are back. And with this, we move on to our next topic, which is the final topic for the conference. Vincent's going to be leading on improving responsiveness of CFS with util estimate.
All right, may I start or should we wait a bit more? Sorry, I didn't hear you.
You're good to start.
Okay, all right, let's go. Hi everyone, I'm Vincent. I'm working for in the Power Kernel team. And today I'm going to show you a bit some research that we've been doing for the mobile application and how the mainline kernel is responding to interactive task. What we mean by interactive task is task where you cannot really predict the behavior and for which the util average doesn't work very well. So I'll start with a bit of history. A couple of years ago, my colleague Douglas shared the RFC about how to improve schedutil, and he introduced a concept that we're going to be reusing today. That concept is to use utils to detect when a task is getting bigger. Utils basically holds the last value of util average at the DQ of the task. So it gives you basically the highest value of util average that you can get, so you can make better placement decision and frequency selection. So what it means that you can observe if util average is crossing the utilest value, it means that the task is getting bigger than previously thought. And so if it happens, it means that the previous placement is wrong, that the frequency selection is wrong, and we need to react to this. Originally in this presentation, Douglas wanted to use this thing to improve the frequency selection. So it was really at the schedutil level. And the idea was to try to cover for some util average issues that he observed, if I recall, mainly due to some lost idle time. So as you can see on the top graph here, yeah, there is a drop into the util average, and it leads to a drop in the util frequency. So we introduced this way by detecting when we cross the utilist boundaries to add a boost and to improve the frequency selection. So this year we've been working on some workload, and one of which is a benchmark, a PC mark, the Web2 part, which is, well, basically just a very simple browsing usage. You are on Android and you just load the web page and then you just scroll down. We've been comparing how Walt performs for such thing versus Pelt. So Walt very quickly, that's the way that Qualcomm is evaluating the task utilization. And we found out that for such task, when you've got a task which is suddenly getting very big, well, Walt is way much more responsive. And the outcome of this is a way better benchmark result, a way better user experience. So now the idea was to reuse the original idea from Douglas, but to put it at the task level and to create a new signal that can be kind of a boost, a ramp boost. The concept is exactly the same. You look per task when the util average is crossing utilest. If it does, it means that we need to react. We need to potentially upmigrate the task. We need to change the frequency. So you have a virtual boost signal that can trigger misfit. So the flag that will re-enable the load balance on EAS system to upmigrate a task to a bigger CPU and also raise the frequency. The boost value that we picked is very simple. It's just a difference between utilest and util average times a factor that we're gonna talk about later on. That simple relation helps to avoid to have any margin.
And the longer you crosses utilized, the most boost you're gonna get. So it's interesting because if the task is just slightly overreach utilized, well, the boost will be really small and it will have very few impact on the whole system. But if you have a big task that suddenly becomes very huge, well, the boost will have a lot of effect then. So we've been looking for evaluating this solution. So for this, we use the Pixel 4, which is, well, kind of a 2 years old phone now. And we use the mainline-ish kernel. So I say mainline-ish because it's still the vendor kernel, but with a lot of backports to have at least the scheduler part to be as close as possible from mainline. The idea was really to evaluate how to make mainline better for such application. So we tested that kernel without any vendor value add, without any Android hints or boost. We run 30 iterations of Android of PCMark, sorry, to be sure that we have something that is statistically significant. And you're gonna see some energy estimation on the following graph. So the energy estimation are based on the idle states and the frequency selection and the energy model declared for this platform. So it's interesting because that's the values that have the kernel to take decisions on the placement for the task. But we know that it has a lot of limitations. For example, some idle states are hidden from the energy model, or we know that power domain is shared across several CPUs, and this is not something that is described into the energy model. So it's interesting in terms of comparison, but it's not something that we can take as an absolute value. So the first test we've been playing with is the data manipulation. It's a simple test from PCMark where you just draw a graph and then you just scroll. And what we've seen with this is that applying the boost doesn't change anything in terms of both performance and energy. It's still quite interesting because it shows here that the boost won't just randomly add some boost anywhere. It's really when it's needed. And in a such test, for example, in a such workload, there's no big changes in the task size, so there's no need for any boost. So yeah, we are not wasting any energy. However, if we apply the same thing with the Web 2 that I previously introduced, so the web browsing part, we'll see like substantial changes. So in blue, you have the performance improvement that we managed to get across different factors. So remember, the factor is what I described previously. The boost is equal to the difference between util and util average times that factor. So of course, the bigger the factor, the best performance you have, but the biggest is the energy penalty you have to pay. So it shows how effective it is for such workload and what it can bring to the mainline kernel. We wanted to go a bit further with that boost, and there's another component to utilist that I haven't described yet. This is the AWMA. So what is it is when you have utilist enqueued, so the value which is read at the task DQ, this value is hold. So basically when you have subsequent, small activations, the utilist EWMA will hold a bit the utilist value, and then the utilist value is just the maximum of the enqueued and the AWMA. So this is interesting. If the task becomes suddenly way bigger, we can anticipate this because we hold the AWMA. So that's the green part where it's actually a win of using the AWMA. The downside is the gray part here where we just wasted a lot of energy to hold the utilist value while the task was small enough to use probably a smaller CPU or a higher frequency. What is interesting here is that the green part where the EWMA component is interesting is exactly where the boost I've just described is having an effect. So it's meaning that when the util average crosses the utilist. So we are hopeful that such boost could replace this signal. So we wanted to evaluate a bit how the AWMA, removing the AWMA performs. And we actually managed to get some unexpected result. We hope that by removing the AWMA, we would have a tiny drop in performance and potentially a tiny drop in energy, but it's actually the opposite that happened. We have some ideas about why this is happening, but it needs to be investigated. In any cases, it's really interesting because it shows that with the boost, we are probably in the right direction, and removing the AWMA is the utilized EWMA, sorry, is not harmful for the performance of the system. So yeah, that's it for presenting this this boost. So now, if anyone has any comment, ideas, any benchmark suggested to make sure that it doesn't hurt anything.
So I have a question. So one of the things we do in Android to make Pelt more reactive is by tweaking the Pelt half-life. Is this something you have tried? Have you compared just like making the Pelt half-life shorter versus having this boost, or?
I haven't compared it yet. Yeah, we thought about having a look at it, but yeah, the problem with the Pelt half-life is that, well, it applies to all the tasks. You have no control over it. Well, here you can easily imagine like to add some control to the boost. It's also compatible with uClamp. And also, well, if you move the Pelt half-life, well, it works in one way, but it also works in the other way. So all the frequency will drop faster. So this is definitely something, and I kind of expected that question. So yeah, this is definitely something we need to evaluate how it compares against the Pelt value. The thing is that also it fits quite nicely into the scheduler. Because we already have utilist, we already have util average. Well, currently Pelt is hard-coded, so that's also what pushed that direction.
Okay. Okay. So yeah, and I understand. I think it's the crossing point of utilist and the what you call the utilist and util average is an interesting. Like, it's a very interesting point. But
yeah, it's really saying we base all our task placement and frequency selection based on utilist. So if suddenly the estimation is wrong, we need to react.
Yeah.
Yeah. So I'm glad that you're analyzing Vault because the things that are implementing are what I implemented while I was working on Vault. So I'm glad to see that you see the benefits of it. Having said that, all of the code is GPL, so it should be fairly easy to port it over to Pelt. And that's something I'm definitely interested in looking into. And to give some more context on utilist and the issues you're seeing, one problem with utilist is we forget utilist value too quickly. But if you try to remember it for too long, you have the problem of in your graph, you had a green area where you're wasting energy, or not green, the gray area where you're wasting energy by holding it up for too long. And if you just look at the GPL code that's published for Vault, you'll notice that it is basically keeping a heat map of your different util values across, of say, a 1024 scale. You split it up into buckets. I'm just making up a number, let's say 10 buckets. They're basically saying in this particular range, have I ever had util fall in this value? Like has util average ever fallen in this bucket? And you just kind of remember that, and that will also help you jump faster instead of going just by the factor between like what you consider the boost, where util average is exceeding utilist. But yeah, I'd be more than happy to kind of like work on this too and try to port what's there in the code that's published outside and see how it compares to what you're kind of working on.
And one question from my side, like when we come up with a solution to change the half time of Pelt, isn't this actually fighting against UTLS and not only the EWMA problem with the boost? I mean, if the signal can ramp up much faster, then why do we need UTLS at all?
Well, define faster, right? I mean, UTLS just give. I mean, UTLS allows to do better task placement and frequency selection when you place the. I mean, when the task is activated, because you know already. So I don't think that you can get rid of UTLS just by reducing, sorry, the period of life.
Because we have to do the synchronization against the CFS run queue before we do task placement decision on it, right? And like a faster ramp up would also mean a faster decrease, and that's why it won't bring anything. We still need UTLS for this kind of problem. Okay.
Yeah. You need so if you have like a long that was the original use case, I think, for UTLS. It was like long sleeping tasks. If you have a task that's sort of that has a periodicity that is misaligned with the period, then you quickly forget, and then the placement the placement you do is going to be wrong. The task placement in particular. The frequency selection is not too much of a problem if you have a fast like the 8 millisecond half-life for pelt, then you will fix up the frequency selection quickly. But for the task placement, when the task wakes up after a long sleep, then if you forget what the value was, then you will pick the wrong CPU, and then you have to migrate and all that. So it takes a little while. So I think you would still need UTLS.
And I think the problem Vincent is effectively seeing is that UTLS is still getting forgotten too quickly, and that's what really needs to be solved. Vincent, you were. Yeah.
Oh yeah, I mean, you have two questions that you have tested several factor level. Which one will you select and why? Because that will become a heuristic. And the other one is that, do I understand correctly that we can replace the EWMA by this?
So
I mean, I'm afraid about accumulating one feature, another one, then another one, and at the end we end up with the 10 additional feature on top of that. So would it mean that we could replace AWMA with this boost?
So that's so for the second question, yes, that's the hope that it could we could allow to get rid of the AWMA. That's that was this slide. So because the AWMA helps on the green part, but if we have already a boost that helps at the same part, there's no real need for using the AWMA. And yeah, the downside is that's a virtual boost, right? So yes, there is some heuristic here involved as per the factor, and this is currently sadly just based on test.
Do you have comparison with Vault after these changes? You are trying to have graphs and show how quickly it reacts.
I don't have the traces here.
Okay. I'm kind of curious how much it kind of brings it closer to that implementation.
Vincent, maybe you can also mention when do you apply the boost? It was for those more long-running tasks, and you can't really apply the boost on top of the util average all the time, right?
Yeah. So in the proof of concept we developed. So yeah, it's when you read misfit, when you set or not misfit, or well, more generally the CPU overutilized, and when you try to get the frequency, when you get the value of the utilization to set the frequency. And the boost is of course updated only during a tick, because that's the only place we really care about. When we enqueue the task and the average, the util average is updated well, we do not expect util average to be bigger than utilest, so on the left. And when we dequeue the task, unless this is for migration, we know that, well, we're going to have an updated value of utilest, so the boost doesn't make any sense anymore. So the boost is set only during the task tick. right? Any
And
other questions? Yeah, sorry.
And this boost with the IO per task IO boosting, this look two input for the same kind of feedback on the schedule and so on. I mean, do you think that could be merged in one boost value? Or?
Yeah, probably. I mean, clearly, there's no point in adding both. So we should probably just take the max of it.
Maybe like from an implementation standpoint, since we haven't finished those the IO weight implementation, I think we should keep them separate, but keep this in mind that essentially they're doing the same kind of thing. But before we talk about those things, we have to have like a working implementation for IO Boost, which we can share.
No, my point is that both they want to boost the frequency based on something that we are not already aware that is not already reflected in the task statistic. So that's why they seem to be pretty similar in the result, maybe not for the input, but in the result they want to add some kind of a additional utilization for the CPU and the frequency selection, for the CPU selection and frequency selection.
Yeah, definitely there are some common ground. Well, when you apply when you read the virtual, because well, the IO boost would like also to increase the frequency selection and to also potentially up migrate. So at those two places, like at some point, the two boosts should be aggregated to take the biggest of both.
And just, I don't know if you have done similar tests, but one problem with the utilization and per task utilization is that when two tasks are fighting for the same CPU, their utilization can decrease because they are waiting for running. I mean, how this can impact your boosting? I mean,
so for in that case, the frequency should already be pretty high, right? Because the CPU is fully utilized. So hopefully you don't see the problem as much. But yeah.
Okay.
Yeah, probably. And in the the idea here is also to just aggregate when you have several tasks that need boosting on a single run queue. You just take the maximum of the boost at the run queue level.
I was going to ask Vincent, because probably there is some confusion. The IO weight boosting is more kind of virtual, while this one we are going to use also for the energy estimation, isn't it? Or
there's no need to use it for the energy estimation because I mean, you're talking about for the task placement, right?
Yeah.
So there's no need to read it here because you're gonna estimate the energy at the task placement, and when the task activates, and when it does, there's no need to use the boost because there's no boost at that time. We know that due to the last activation, the utilist is already updated, so there's no boost needed here.
okay, so this is going to be also like the IO weight boost. It's not affecting the energy estimation at all.
This one, yeah, for sure. Yeah.
The IO weight boost very much should impact the energy model, right? There's no reason why it shouldn't.
Well, we don't account that task as the real utilization, right? We account it as a small task, the real util average.
Yeah, but
of this
the
boosted
fact that
task.
there is a boost, the fact that there is a boost associated with the task will result in the frequency in which this task will be placed. You know,
the frequency selection.
Right.
Yeah, the frequency selection is true, but the energy for this particular task is taken from this task util, the real one, not the boosted value.
But the frequency at which, I mean, we estimate both two things in the energy model, right? The time that the task will spend on the CPU. That's based on the utilization. But we also estimate the frequency at which the CPU will be running. And for that, we account for things like uclamp and all of that stuff to make sure that we predict the frequency selection correctly in the energy model. So I think the boosting should be accounted in that part as well.
So the boosting will be, but we are not going to measure how big the task is when we ask for this energy calculation. It will be from the real util, not the virtual.
The time needs to be correct, but yes.
Yeah. So these two virtual. So these two virtual new metrics will be taken into account only for frequency, while for the energy there will be always those small tasks. Let's say task 10 util will still be 10 util for the energy cost. But it will drive the cluster frequency higher, so we will pick up higher power number for that cluster.
Exactly. We just need the performance state prediction needs to account for the boost. That's the only thing I'm saying. So I think we agree. Good.
Yeah, I think we will have the same problems like with uclamp min today when it comes to those decisions or not.
Exactly.
There's already a separated path in the compute energy function. Right. 3 minutes. Any questions for the 3 minutes left?
Not related to this talk, but is there going to be a BOF for the scheduler stuff or no?
What? Sorry?
So the answer to that is there are a bunch of hack rooms. If you get people together and use one of the hack rooms, these are always available. And I would highly recommend that, right? The goal of this session is not to solve the problem entirely, but get a start and continue it on mailing lists elsewhere. And hack rooms are a great place to go and continue discussing that. Any more questions for Vincent?
Maybe one thing regarding this hacking room. Is there a way to send to everybody that will join an hacking room for one special topic? I mean, for example, for this one, how can we broadcast that we'll continue discussing this boosting value?
So do you have access to the matrix instance?
Maybe, I don't know. I'm not sure. Yeah.
There's. I'm going to paste the link on.
I think I put the link in there at the top of the public to share notes.
Right. Steve, what's the official way to coordinate? I mean, I was going to go with the unofficial way, which is go on to matrix and figure out a time.
Yeah, I guess we really don't have an official way. That would be a good idea. Besides, the matrix, that we're expecting the matrix to be working, and that was somewhat of a fail. But we should have like an announcement thing, maybe. I wonder if we should post something up. That way people could, say, hey, meet here, and we could put up like a bulletin board somewhere. I'll ask.
Okay. But at least for the time being, right, the matrix instance is just a great place to coordinate and figure out.
Okay. Not working for me, by the way, the matrix instance. I still get communication error with the home server.
Are you connecting from the desktop client or the web client? Because the web client seems to be working, but I'm also having issues with the desktop client.
The web client, I just clicked on the link from James' email, put my username and password, and keeps giving me the error, cannot communicate with the home server.
Yeah, it gives M unknown. I can't get in via web client either.
By the way, when you type in your your username, replace the @ with a period for your email. You've done that, correct?
It took me some time to figure out this. It's written just at the in the logging window, but yeah.
Yeah,
that
yeah,
was my
we joke.
problem as well before.
A few of us were saying, yeah, people, or James is like, oh yeah, it's simple. People will easily be able to figure this out. We're like, no, I think it's going to screw up a lot of people.
Well, it's auto filled in, right? So
yeah.
Yeah, I copied from James's email when I noticed that.
Yeah, it's not auto filled in for me. I didn't know that I needed to replace it with a dot, but I don't think it's auto filled.
Well, James owes a lot of the program committee, what's it called, beers, because we had a bet that it would screw up a lot of people, and he said it wouldn't.
Clearly, James had a higher opinion of us than we do of ourselves. Okay, thank you, Vincent. Thank you, everybody, for joining into this microconference. This microconference is not possible without the speakers, obviously, as well as everyone else who joined into the discussion and helped make it productive. I hope it was productive. You know, there are many topics that felt unfinished, and I think that's great. We should probably continue on using a hack room and making progress there, continue on the mailing list. I would also like to take the time to thank Daniel for really running this show, Vincent, Yuri, and Chris helping out with the organization, and of course the LPC committee and our sponsors for helping out so much. Oh, Daniel's here. And your audio is not working.
To invite
And then there is a keynote right after this. I think you have to go to the referee track to attend the keynote. Okay, thank you very much, guys. See you on the mailing list.
and please join the real-time microconference tomorrow.
And the Tracy one after that. Aha.
We will be there.
You are currently the only person in this conference.